this important workshop, the 15th annual AfricaArray Scientific Workshop. 15 years is a long time, of course. A lot has been accomplished over that time. And I want to acknowledge a number of folk that have assisted in putting this together. I'm sorry that Professor Ray Durham is not here today. He had approached me already a while ago. Professor Musa Mansi has also been assisting in putting this together. I would like to recognize the head of the school, Professor Julian Drennan. Thank you, Jill, for all of your tireless efforts in promoting the excellent work of the School of Geosciences. And Stephanie, as well as little Stephanie, I see Stephanie has been accompanied here with.
Can I just come? You're a bit soft. So
yes. Do you want me to get closer there? I can.
Sorry. Oh, move your chair. We should still have you in the video. It's
okay. Could somebody just organize this properly?
Yes, come stand. Sit. There. And over here. Okay.
Do you want the camera here?
It's fine. So I think the camera is actually the projector, so it's getting everything. So if you sit here, it'll still pick you up.
I see. Okay, terrific.
There.
Good.
Thank you.
Marvelous. So colleagues, this is an opportunity really for the students and postdocs to showcase their work, and it's an important part of the scientific process to have this chance to do so. And unfortunately, we're right in the middle of a pandemic, which has made it quite difficult. It would have been quite an extraordinarily difficult passage of time of the past couple of years to progress with your work, but this type of interaction is just so important, and I commend the organizers for putting this together. I've looked at the program. It certainly looks very extensive, very wide-ranging, and an engaging workshop. I want to say that this is really fantastic. With the international participation as well. And I welcome all colleagues who are joining in from various parts of the country as well as from international destinations. So I remember being a student too many years ago now, and it was not always easy to stand up and defend my work and in a public audience in the presence of senior folk. But yet that is very much a part of the academic process, to be able to subject your work to peer review and to be able to defend your work, but also to be open to other ideas and other interpretations of your work. So this type of engagement is extremely important, and I sure hope and long for the time when we can begin to interact with each other in more human ways rather than just simply through the use of technology. I sure wish that I was a student again. I think it certainly is an exciting time to be a student. Being the Dean of Science is actually not an altogether easy job, Stephanie. If somebody comes along and twists your arm and asks you to be Dean, please say no. It really is a hard job, but I say that kind of tongue-in-cheek because I found it very necessary to step up at this stage of my life to heading up the Faculty of Science here at Wits University, which is quite an amazing privilege. I do want to say that today marks exactly 2 years since I've been Dean of Science. It's had its lows. It's had its ups, many ups indeed. Wits University is certainly a very engaging, intellectually very stimulating, certainly very argumentative institution. And I think you as students and postdocs should feel very proud to be a part of this great and incredible institution. I saw it fit to be Dean of Science at this point in my career because it is essential that one works in an environment that is supportive and that is appreciates the value of science. Society often utilizes science and the outcomes of science in ways that society does not always appreciate and understand. And so you do need people that work hard, tirelessly, often behind the scenes, to ensure that we create the environment that ensures that science thrives. And so yes, 20 years from now, if you're asked to be the Dean of Science, you should think about that carefully. I think it's wonderful to be immersed in an environment where you can think solely in terms of your science, but if you could be the greatest scientist in the world, Nobel Prize winning type of scientist, but if you're living on an island unto yourself, then it does not help. You have to be interacting and engaging in a broad environment that supports that science. So you should always work tirelessly beyond just simply your own research endeavors to contribute to the wider conversations around the importance of science in society. And I do want to encourage you to think about your role as a scientist as you enter the big wide world of attaining a career in science. So I would say that obviously interacting is important. You cannot work on an island. You cannot work in your bedroom connected to the rest of the world through the internet either. So that has to change, and I sure hope that we're going to move in a direction of greater interactions, face-to-face interactions in the coming year. Now, WITS has mandated a vaccination policy that starts on the 1st of January, and I sure hope and expect that all students and all staff will adhere to the policy. As Dean of Science and the representative member of the senior executive team, it's my responsibility to oversee the implementation of the policy. So I will certainly be quite firm in ensuring that the policy is implemented. Because this pandemic is here to stay, colleagues, we cannot hold back our lives and our own progression, especially the progression in your young scientific careers, because of COVID-19 and its many different variants as we've encountered. So blended approach to our work as scientists is certainly here to stay. I do not expect that we'll go back completely to face-to-face, but where it makes sense, we've got to make use of online technologies. But certainly when it comes to scientific collaborations and discussions, engagements, arguments, debates, and so on, face-to-face immediacy is certainly preferred, and we have a better way of progressing. There are advantages to online, there's no question about it. In some respects, I've attended many meetings this year from a General Assembly of the International Union for Pure and Applied Physics that took place in Europe early this year, to a seminar that I delivered out at in Berkeley in California, another seminar out in Atlanta in Georgia. Next year I will be in Copenhagen, Denmark. But I've accomplished all of that without adding to the carbon footprint. I was able to save costs for my own personal research or the faculty budget. I certainly saved on my time. I was able to continue to be Dean of Science whilst I was engaged internationally on all of these matters. So you could imagine that we do have advantages. So we've got to think carefully about the future of work, the ways in which we will engage with each other into the future. I do not think it's a binary situation, that it's either or, that it's either fully online or fully face-to-face, but we've got to find a happy sort of medium and compromise in between, where we enjoy the benefits of all worlds. So I want to commend the African Array. I've glanced very briefly about the mission of the Array, and it's a coalition of support from many different sources, including from academia, from government, and from the private sector, not just here in South Africa, but broadly impacting on the rest of the African continent. But I'm delighted to see the number of international partners involved in this and focused on broadly on earth sciences, geology, in particular, atmospheric and space sciences. And well done to all of you good colleagues that have made this happen over the years. Now, talking about over the years, WITS turns 100 next year. In fact, the University of Witwatersrand was established on the 1st of March of 1922. So we're already in our 100th year. We should already be celebrating our 100th anniversary and not necessarily wait until the 1st of March of next year. The origins of the University of Witwatersrand is is really in the mining industry, originally in the South African School of Mines that was established in Kimberley at the time of Cecil John Rhodes at the turn of the previous century. And that was in line coinciding with the discovery of diamonds out in the Kimberley area. And subsequent to that, following the gold rush to the Witwatersrand, to Johannesburg, is when the predecessor of the University of the Witwatersrand moved across to Wits, and the university was formally established in 1922. So as students of the School of Geosciences, you should feel very, very proud to be associated with that history, because you are really part of the genesis of this fine institution. But the times are very different now, and it's important that you begin to think about how life has changed over 100 years. Of course, the most important change has been the dawn of our own democracy here in South Africa in 1994, where we have important challenges addressing issues of inequality and poverty, sheer abject poverty that we experience in South Africa and more broadly on the rest of the African continent. So whereas in the past a lot of mining was associated with the gross exploitation for capital gain, for personal gain in most instances, now lives do matter. Of course, lives always mattered, but it didn't really matter to those who are in power, those who control the resources, and today, and those who exploited individuals for their own personal gain. Today, as graduates from the School of Geosciences, I certainly expect that you will think very carefully about the important role that you will play in changing this environment to ensure that the benefits of this massive sector is experienced for all concerned. So part of graduating from this university is to think about the impact of your work, not just to simply advance your own careers personally, but also to look at ways in which we can better live our lives in our country. So it's not just aspects related to capitalism and the way and wealth accumulation by a handful of individuals that has occurred over the past 100 or so years, but it's also in the environment. We need to take the environmental matters very seriously, and the mining sectors always had an impact on the environment. I'd like graduates from your school to think about ways in which we can work more harmoniously with nature. This is very essential because we bequeath to a future generation of people a very difficult environment brought about by human interventions and interferences in the ways in which all organisms on this planet live their lives. So we ought to be very concerned about about environmental degradation and the impacts that has on climate change, and you need to think very carefully about the ethical applications of your work in broader society. I think I've already touched on issues around economic development. I think we've got to think more carefully about how the mining sector can impart greater, have a more positive impact on local communities, not just simply the sort of inherent colonial idea was to exploit the gains of the earth and to transport that to far-flung places and to be completely disregarding of local development. I'm sure you'd agree that in this day and age, it's just not possible for us to think in such a cavalier way. We've got to think about new sources of energy, invariably the mining sector, geology, the geological sciences, geophysics, geochemistry, and all of the related earth sciences, including Earth observation, geographical information systems, and so on. Atmospheric sciences would all play a role. We need to think in terms of the only planet that we know. We just have one shot at this precious planet that we live on. So we've got to look for cleaner processes for our mining, more efficient ways to prospect, to mine, to extract, to process, and to beneficiate ultimately for broader society. And of course, the scientific rigor behind all of this is extremely important. It's not just simply gross kind of economics here, but it's the science behind this. And this is why we're at a university and not in some other university of technology or artisan training. It's a science. It's developing a deep understanding of how the environment came into being, because by understanding the past, we hopefully have a better way of planning for the future. So I think that the future is very, very positive for students and postdocs in your category, in your age group, in your cohort rather, because they are. It's not the geosciences of 100 years ago. It's the many possibilities of introducing modern techniques, better use of data, using artificial intelligence methods, ultimately to develop a predictive capability for the things that you're doing, which are extremely important for society. So I do want to leave you with my thoughts that the future augurs very well. I think you've chosen well, but there are important things for you to think about in ways in which your discipline needs to address issues of societal importance. So in closing, then, use of modern methods, going beyond just simply studying and pursuing your research endeavors for personal gain, thinking very carefully about societal benefit, protecting the environment. And of course, AfricaArray is all about developing the new generation of scientists. So getting involved in student training and exciting a new generation of students for the future, very important. I cannot say that academic jobs are plentiful. That's not just a scourge in South Africa. That's a problem worldwide. So some of you will pursue jobs in the academic sector, which is a wonderful, wonderful place to be. But unfortunately, it is a highly privileged place to be. So do cherish these times whilst you're here at Wits University. But if you're an academic or a researcher or a teacher in this area over the next decades, then I would suggest that you have a lot of exciting possibilities. If you join, if you get a job in industry or join some commercial concern, or become a consultant of some sort, or become be employed in a government agency, you also have an important role to play, because I started off by talking about society often using results and outcomes of science without necessarily understanding the origins of that. And it's important for us all to be fully engaged in society, to have society understand the importance of science, and for you to play that role to ensure that wherever you are, in whatever it is that your future calling is, that you will play your part in ensuring that we have a sustainable scientific environment where science can thrive for the benefit of society. So colleagues, I wish you all the very best. Dr. Enslin, I wish you and colleagues all the best for the remaining 3 days. I see that it is a very exciting workshop. I unfortunately will not be able to be here for the remainder of the time. It's the work of the Dean that is calling yet again. I've got to rush off to another meeting. I wish you all the very best. Thank you very much indeed. Okay, she's on. Yeah, thanks, Natasha.
Thank you to Prof. Chetty for that. I'd like now to hand over to Dr. Jill Drennan, Prof. Jill Drennan, who I believe is online here. I want to try and switch microphone. Can I be heard? Is it good? Thanks. Okay, Jill, I see you've shared your screen. Yeah. Whenever you're ready. So just a quick introduction. Prof. Jill Drennan, as most people know, is the head of school She has been a mentor to many, many students, and I'm sure many of the colleagues in the School of Geoscience as well. So yeah, when you're ready, Prof, please take it away.
Good. Well, thank you very much to you, and thank you very much to our Dean. I know he's had to dash out, but thank you very much to
Jill,
him.
you're muted.
No, I'm not.
No, you're not muted.
No.
Sound guys coming.
Joel, we can hear you fine.
Reese, you can hear. Can everybody in the hall hear?
No, you need to have the speakers turned on.
My speaker's on as high
No,
as it'll go.
not Jill, the people in the room. They need to hook the laptop to the speakers.
Sorted, Sue.
It's sorted, thanks. Sorry about that, Prof. Good to go.
Okay, no problem. Always good to have a false start, you know, kind of warm-up session. So thank you very much to everybody that's been involved in the organizing committee. I would like to echo the Dean's words of congratulations to the organizing committee. Honestly, guys, you've done an amazing job under extremely difficult circumstances. We've had to shift the dates, we've had to shift venues, we've had to go you know, into dual mode, and yet the organizing committee have done that, and they've done it not just okay, they've done it excellently. So thanks to all the students who've helped and who've been a part of it. And earlier, before the conference actually started, Professor Ray Durham and I were just chatting, and I was saying how excited I am as the head of school to see the next generation of geophysicists, of earth scientists, of geoscientists, taking the reins. This is the 15th year of the AfricaArray workshop, and it wasn't without great effort that Ray and his colleagues got it started 15 years ago. But now the next generation are stepping up, and I want to applaud you for taking up that challenge and for dealing with all the difficulties that you've had to do. So honestly, I think that everybody in the auditorium and all those online should just give the organizing committee a round of applause. Please give them a round of applause, because they've done some fantastic work under difficult circumstances. Come on, give them a round of applause. Oh, what a boring audience. But thank you very much to everybody for giving up your time. Thank you too for those that have come and joined either online or in person to be a participant, to be a presenter. Without participation and presentations, the workshop could not have continued anyway. So thank you to everybody for being willing to present and to be part of this amazing event today and for the next couple of days. And I think that one thing that Africa, there are a number of things that I want to draw our attention to, or just remind us of. As geophysicists, you're all very familiar with this, but I think one thing that AfricaArray really, really does well is it promotes scientific exchange, both within our continent, but also internationally. And I think that scientific exchange is something that's really, really important, and something that we need to foster. There's also been an amazing history of capacity development. And I think that it goes without saying that without this capacity development, we would not be doing some of the things that our Dean has just encouraged us to do, to be looking after the future of this planet. He mentioned that we've got one shot at it. And through AfricaArray, we've done an amazing amount of capacity development, and we're contributing to the correct and best practice that we can do at the moment throughout Africa as a result of the training and of the workshops and of the field trips that AfricaArray run. Thanks also to our teams of geoscientists that are promoting the use of data in science. And on that note, I just want to take a short little step aside to congratulate the team that won the the integrated cross-disciplinary team that won the Data in Science National Science and Technology Forum Award, the South 32 Awards. Some of you may not know, but the team comprising of Ray and Musa and Sue and Gordon and Steph, Glenn and Grant from geology, together put in a motivation for and a nomination for the award, and they were the recipients of this very prestigious award. I also want to congratulate Ray for being awarded the Lifetime Award by the National Science and Technology Forum. And that is a real feather in your cap, Ray, and we're very proud that you were nominated and that you were awarded that Lifetime Award. So the School of Geoscience is very proud of them. Geophysics must be very proud, and AfricaArray must be very, very proud of these two awards, the Data in Science Award and the Lifetime Award. Also, I just want to say that, or make mention of the event on Friday. I'm sure that you'll hear more about it during the proceedings, but Friday, as I understand it, there is a special function across at the Origin Center in the Tapestry Room, a chance to get to know each other, a chance to network. And so I do encourage as many of you as possible that can participate in Friday to please do so, to join the organizing committee, to join the team there on Friday, and to just celebrate the amazing accomplishments of the AfricaArray program. So thank you very much for that. And without further ado, can I just remind you to please observe all protocols. I know that you know where the bathrooms are. You were told that at the start of the meeting. But please do remember to wear your masks at all times. Please do remember to sanitize and wash your hands as often as possible. And remember to socially distance. That might be a little bit difficult during the tea breaks and whatever, but please do your best to prevent any kind of infection. And so with that, thank you very much. And I look forward to hearing how the workshop goes. Thanks, everybody. Enjoy the day, enjoy the days, and hopefully we see you Friday. Bye-bye.
Thank you for that, Prof. Drennan. It was an honor to hear from you. I'd like to move on, because we're a little bit, well, we're actually on time, move on to the first technical talk, which will be given by Professor Sue Webb. And with the title, Large-Scale Investigations in the Bushveld Complex and the BVDP ICDP Project. Thank you, Sue.
I'm trying to share my screen. Is it working? No.
Yes, we can see you from this side.
Can you see my PowerPoint?
Yes, we can. Thanks.
Okay, so, and is it full screen?
Yes.
Okay, excellent. Okay, great.
Thanks, Sue.
Very excited, and thank you all very much for organizing the conference. I'm just thoroughly impressed with how everyone has done. And I remember the very first, when we started AfricaArray back in 2003, 2004, when Paul Dirks and I and Andy Nyblade were all writing proposals like crazy and going to meetings all over the place. It was really an exciting time. And to see it come this far is just really incredible. So I've obviously been involved with Bushveld scientific work for quite a long time. And I just want to state what BVDP is the Bushveld complex drilling project of the ICDP, which is the International Continental Scientific Drilling Program. And I'll get to that a little bit later. So one of the things that's come up in the past 10 years or so is a new approach to exploration where we look at larger scale aspects of exploration work. And this is something I've been championing for a long time, is to, for example, look at the long wavelength geophysical signatures instead of just removing them as a regional, but to actually model them and incorporate them into our understanding of how the ore body works. So for example, in the Bushveld, we incorporate the actual moho. So, and the reason for this is our targets have become deeper, and the crust and upper mantle and tectonic framework need to be considered in our exploration of the different ore bodies. So we can't just remove the regional when modeling, and especially when ore bodies are laterally extensive. The actual outcrop edges of the Bushveld complex are nearly 400 kilometers apart. And so we need to consider this very extensive feature. And we also need to consider a sequential approach that's needed of forward modeling different deeper sources, subtraction of their contribution, and then applying inversion to the bits and pieces that are left. And this is something that Carol Finn has done very, very well in our 2015 paper on the northern lobe. So some of this work is described in the Ore Deposits book, which is out in 2019. And we have a chapter in there on the Bushveld complex. So the importance of large scale geophysical investigations. I'm just getting the laser pointer on for mineral exploration. And this is one of the points we're making is everybody wants to find another Bushveld complex. And we really need to consider larger scale implications. So where is the Bushveld complex? For those of you that are joining us not locally, I just want to point out where the Bushveld is on the global scale. It's in Southern Africa. And it's this is an example of where the Merensky Reef, which is one of the reefs that is mined, where it outcrops in the Bushveld complex and where it's mined. And some of the more recent work by some of our other colleagues, by Sophia and Rice and Emma and Stephen Barnes. And also to point out where the Malopo Farms complex is, which is right next door to the Bushveld complex. And in fact, any other place in the world, Malopo Farms would be considered, you know, a huge layered mafic intrusion. But because it's dwarfed by the Bushveld complex, we haven't studied it as much. But there are a couple of projects working on it now. So let's look at some of the details here. I want to point out a few features. Sorry, am I cutting out? Okay, I'll try to sit closer. Or maybe I can turn my video off. Would that help? Anyways, okay, so in the northern lobe, I want to point out one feature is this BV1 borehole, which stands for Bellevue, which is in the northern lobe and is a 3-kilometer deep borehole going through the entire upper zone and about half of the main zone. There's also a couple of kimberlites that are in the Bushveld complex. Many of you have heard of the Marsfontein kimberlite, which was an incredibly highly profitable kimberlite, but it sits just outside of the Bushveld complex, depending on where the Rustenburg layered suite goes in this highly faulted zone. The TML is the Tombazimbi Murchison lineament, which is a series of faults and relays coming through the Bushveld complex, which disrupts this area quite dramatically. And also the Palmitgat kimberlite, which is in the middle of the Bushveld. And this is a very, very important kimberlite that we'll get back to later. So this kimberlite is almost perfectly positioned halfway between the western limb of the Bushveld and the eastern limb. The premier kimberlite, or Cullinan, down here in the south, again, is on the edge of the Bushveld complex, but it does contain some mantle nodules, which is quite exciting. So let's look at some of the data we have available. These are the data from the Council for Geoscience, the government data that are freely available. I'd like to emphasize that again, that for anyone who's interested in working on South African data sets, the Council for Geoscience has made their legacy data freely available. And in fact, some of their newer data sets are also available on their website portal. Please go there and make use of that. It's an incredibly useful resource. So this is the total magnetic intensity, and we can see the strong signature of the upper zone of the Bushveld showing up as this red-blue pair, at the inner edge of the dipping sheets or dipping edges of the bushveld. These are all dipping towards each other. Here's the Pilansberg. Here's the northern lobe. Here's the fault zones up here at the top. And you can see there are longer wavelength components and shorter wavelength components. In the Bouguer gravity data, we have the higher gravity values correlate where the edge of the outcrop is, because of course that's where the outcrop will be thickest. And we see the northern lobe mapped out very well, the Villanor portion up here. And we note that the gravity values go back to 0 in the center. But I want you to imagine if the bushveld were completely under cover. And in fact, if it had been eroded a little bit, so that the magnetic signature or the entire upper zone might be missing, it would be very, very difficult to find. We can only see it because on the gravity signature, the edges are actually dipping. If they were flat because it had been eroded from the dipping part, we would barely see the bushveld. And this is to make the point that we could have an entire bushveld complex hiding in the crust under cover that was almost hidden from our looking for it. So we need to be very clever how we use our exploration. So just to look quickly at this argument for a connected bushveld, because it's quite important we understand where this change in thinking came from. Some of the earliest models of the bushveld complex, if we look at this green zone, which is where all the economic goodies are, we see the early models had this connected, and in fact, this is from Alex Dutoit's work. This also shows a connected bushveld, the so-called Lopelith model. And in this model down here, we have a connected bushveld. This is the western side of the bushveld showing the Pilansberg and the outcrop over here. And then on the eastern side, we see it picks up over here. And the implication is that at depth, this is connected. However, in 1959, Cousins, who was a physicist, actually got hold of the gravity data of South Africa across the bushveld complex. And these are the actual gravity anomaly data he used. So this is a profile from west to east across the bushveld complex, from the town of Northam to Oranstad over on the east. And he modeled this as a lopelith, so a connected lopelith. So the granite's on top, a lopelith underneath, and transball underneath that. And you can see the problem with this model is it does not fit the data in the center of the model. So the values in the center go back to our background values, which are almost 0 in the center. And so he used this as a very strong argument to argue against a connected bushveld. And he stated categorically that the geophysical data proves that the bushveld has to have 2 separated intrusions. And he was very adamant about arguing for that. And in fact, if you look at some of the literature of the time, when they recorded some of these arguments by writing them down, some of the sessions, it sounds like they got quite heated, you'll see that he argued very, very strongly for this. And this idea was picked up by Meyer and De Beer in their 1987 Nature paper, where instead of separated intrusion, they used a dipping sheet model where the actual bushveld components are dipping, but they're not connected at depth. There's only granite down here. And this fits the data very, very well. We can see that the actual model data comes right back to 0 here. So first thing we did when we were looking at this is we produced the historical models. Here's our dipping sheet model. Here's Cousins' model of a connected lopelith. And we see that the calculated does not fit the observed, whereas over here, it fits it pretty well, especially down here. These other bits in the middle can be attributed to other components in the center. But what we wanted to look at was crustal flexure. And sure enough, if we allow the crust to flex, if we look at this long wavelength signal that's from the MOHO, and we push the moho, the lower density deep crust, into the higher density mantle, we actually get a component of the gravity signal that is the same wavelength as the actual bushveld itself, and brings the whole signal down to levels that match the data. So this is really an important illustration. It looks like such a simplified model, but it's so important to test these models, these simple models, to see if these long wavelength components can have an important impact on our modeling. And so we were very fortunate at the time that the CAPFAL project was running, and the South African seismic experiment was a component of that. And we had all these seismometers out all over Southern Africa, and we were able to draw a line through these seismometers right through the center of the bushveld. And this is now the gravity signal through the center of the bushveld. And when we look at the crustal thickness there, we see the crustal thickness is actually quite a bit thicker underneath the bushveld, just as we had predicted. So we were definitely holding our breath during this time, trying to see if the bushveld would be thick underneath the center part. And that was kind of exciting when those results came through. So we've made an updated model where we actually combine the connected bushveld with an isostatically depressed crust. And here I've made a 2D model that fits both the teleseismic data from the receiver functions, the crustal thicknesses, and also the gravity data. And this was taken a lot further with by Janine Cole, and she's looked at a number of different crustal thickness models and come up with different 3D models. We've also looked at the SAMTEX data, the magnetotelluric project that Ellen Jones ran and has been published on, and also some new data from the AfricaArray program that some of the students that Ray Durheim and Andy have supervised have also looked at more detail of the crustal structure beneath the bushveld. So one of the students of mine, Janine Cole, as part of her PhD, developed a 3-dimensional gravity model. And this was kind of exciting because she was working with her husband on a program that her husband wrote, Patrick Cole. He wrote Pygmy, which is Python gravity and magnetic interpretation. And so it's a very quick way to develop a 3D model. And these are just slices through this 3D model with quite a bit of detail. Janine is a very detailed-oriented worker. And so we were trying to just get a broad scale picture here and eventually got one out. And here we have a 3D model of the bushveld that fits not only the crustal thickness data, but also the gravity data, and is also constrained by some of the seismic lines. So this is quite an exciting result. And you can see there's still quite a bit of detail in here. This is a very interesting feature here. This is up near Polokwane, and it appears to be a feeder zone, and it appears in every single model we've been making of the bushveld complex. And it appears that this feeder zone, this very narrow tube going deep, deep, deep into the crust, is important as a feeder zone to the bushveld. And it helps explain why there isn't a lot of, say, thermal damage to the subcontinental lithospheric mantle if we're able to bring things up in these narrow feeder tubes. Okay, and then this is another view of this 3D model that's been developed over time. There's different versions of it out there. And again, we can still see this feeder zone that if we're looking at the underside of the bushveld complex now. I mean, the beauty of doing these 3D models is you can twirl them around and really investigate what's going on. So, and I just want to point out here that the code for this, for the Pygmy program, can be found here. And it's also, it's got a GitHub site that you can download it and install it from. So if we integrate with some of the other information from the SAMTEX and AfricaArray, for example, we've got, here's some of the From the Cap Vol project, we've got the seismic velocities or the P wave velocities at 150 kilometers depth. This is the P wave velocity anomaly, whether it's higher or lower than the background. And over here, we've got the SAMTEX or the magnetotelluric data. These will be your resistivities or your log of your resistivities. And you can see a very changes in the resistivity with depth. And so let's get back to this palmicate kimberlite as an investigation of connectivity. We mentioned that all the models we've been able to produce actually allow for connectivity, but we know that gravity data can be ambiguous. And so we have to be careful to say, you know, the gravity data absolutely constrains the Bushveld to be connected. It certainly allows it to be connected. It satisfies all the data sets that we have. But we need some independent confirmation. And we were able to get that from this kimberlite, which is here in the middle. And here it is I think this was 2005 when we went there. And you can actually see a little bit of kimberlite on this one. It's a series of 6 kimberlite pipes. And this one has been mined to about 30 meters. And we actually found in the waste of this kimberlite, after they've extracted the diamonds in the heavy fraction, we found some peroxenites that were exactly like peroxenites in the Bushveld complex from the critical zone. So they had the exact same mineralogy and matched perfectly. So we were able to use that as evidence that this kimberlite has brought up these crustal xenoliths to the surface as evidence of connectivity. And it's interesting, Lou Ashwell has also been looking at some of the issues around the mantle structure. And the Bushveld is one of 4 large igneous provinces that has impinged on the surface of South Africa that we have a record of on the surface. And he's identified 4 plume sites, if you will, of where these have possibly erupted. And the point he's making here is that none of these should, if there's too much magma for this to actually have come from the subcontinental lithospheric mantle. So this had to come from below that because otherwise it would be too depleted. So that's an interesting problem. And one of the things we're interested in is how did the Bushveld, how was it emplaced? What is the emplacement mechanism? And one piece of evidence we have for that comes from that Bellevue borehole core that was up in the northern lobe. This is the record of the bottom portion of that in the main zone from about 1,500 meters down to 3,000 meters. These are the lithologies. The greens are basically norites and yellows are anorthosites and the pinks are granites. So this is basically all just norite and anorthosite, which are the same minerals, just in different proportions. And we see something amazing here. Over and over, we see layer after layer after layer of density values. Now, this is density going from 2.5 to 3.5 grams per centimeter cubed, and density is increasing upwards. This is not what you expect when you're looking at, say, a layer of material that comes in. You expect the denser material to settle to the bottom. So we would expect higher values at the bottom than at the top of a particular layer. So this is quite enigmatic. And we have published a paper with Ben Hayes that we have used to explore one possibility of that, which is where each layer comes in and then kind of dribbles down onto the layer before with the higher density material. So that's our working model at the moment. And one of the purposes is to look at this in more detail with the Bushveld, the ICDP program. So just to summarize quickly, the Bushveld complex is a large igneous province. We know the melt is not from the subcontinental lithospheric mantle. And the other piece of evidence, also from the palmicate kimberlite, is that the emplacement did not take the diamonds out of the diamond stability field. So the temperature never got really hot because we actually have old diamonds in the palmika kimberlite. So they were never out of the diamond stability field. This is also consistent with the gravity modeling. And we suggest there are thin channels with limited feeder zones. All 4 cap-fault large igneous provinces seem to be emplaced in sedimentary basins. So this is something to think about in terms of how these things are emplaced. And we want to consider this as we move forward with our ICDP project, and that pulses of emplacement occur over a short period of time in all of these large igneous provinces. So the Bushveld complex is consistent with an intruded large igneous province. So one of the questions is, why don't we use seismic data to investigate the Bushveld complex? And well, we would love to. We don't actually own any viper sizes, but Muzamanzi has recently, as part of his seismic work, purchased not only a large weight drop, a 500 kilogram weight drop, the whole thing is 2 tons in total, but the drop itself is 500 kilograms, and also some new land streamers. So we should be able to collect some really interesting data on land very, very soon. So we're looking forward to getting that out in the field. And I just want to congratulate Musa and Ray for getting this equipment into the department. And one of the projects we want to look at is actually to do some seismic data across where we're going to be drilling with the ICDP. So this is our logo for the Bushveld drilling project, and it's picking up on the themes of these beautiful chromatite layers that we see at the Dwars River. And this project has been a long time coming. It was kind of overtaken by Ray's project when the earthquake happened, and so we kind of took a back seat, but it's taken us a while to get all our ducks in a row also, with a large number of donations. We already have 7 kilometers of core donated to the Bushveld project that are housed both at Bloemfontein at the University of the Free State and also at the Council for Geoscience. We have another couple of kilometers of core up there, and we're negotiating for another bit of core. And so we're only going to have to drill about 3 kilometers of core in 2 1,500-meter boreholes in the eastern limb to complete the project. So a lot of core has been donated. One of the things we're very proud of is that the core will remain in South Africa, and the Council for Geoscience has agreed to host the core and archive it for posterity, and researchers will have to come to South Africa and request core from the council. So we're very excited that this will be a resource for many, many years in the future that the council will be archiving. So into the future, targets are often poorly resolved with depth, and so we need a reflection seismic campaign, for example, to help resolve the thickness of the Bushveld and some of the details of it. The teleseismic data and the imaging we have is still very, very fuzzy, so reflection seismic would be a big help. The ultimate goal might be a 4D model of the Bushveld complex, which examines its current 3D geometry and think about it in time in a tectonic context going backwards. What can we learn from looking at that? And then this model would allow us to test the emplacement models and postulated deformation events, ensuring they're consistent with our large-scale geological observations, rheological responses, and age constraints, and help us to target new areas where bushvelds may be hiding in areas that are more deeply eroded. So our current working model is a plume of the staging chamber as our best working model. And I do want to emphasize the staging chamber is a new piece of work that Janine Cole is currently writing up a paper on, and we should be hearing back on that one soon. So there's a lot of work going on in the Bushveld complex. This is only a small portion of it. There's legacy seismic data. There's lots of physical property data. There's hyperspectral data. We need to incorporate the mantle variations and deep crustal variations. We're looking at staging chambers and feeder zones and mantle interaction. And our Blue Skies project is looking at the recording of the Earth's magnetic field and its magnetic reversals in the main zone of the Bushveld complex. We're very excited about that, and that's inspiring the development of our physical property lab. And there are many other projects that other colleagues are working on, so please discuss these with us if you're interested. Across the top there is a very, very complicated and interesting seismic line that Stephanie Enslin is working on, and should be very interesting to see where that goes to. And just to finish off and to say thank you to all our many, many, many sponsors, Anglo American, Anglo Platinum, etc. There's a ton of people that have come together to provide information on all these different projects. So I'll leave it there. Thank you very much. I think I'm almost on time too. Shall I stop sharing?
Thank you, Sue. There are a couple of questions in the chat. We do have a few minutes for, a couple of minutes for questions. If anyone has questions in person, could you make your way up here and we can get those going. But for now, see, there's a question from Wesley Harrison. It says, how was the Samtex data integrated in the 3D model? Was a joint inversion calculated? And is there any plan to integrate with the current MT project running across South Africa?
Yeah, thanks, Wesley. Thanks. Am I unmuted? Yeah. Thanks, Wesley. Thanks for that question. The problem with the Samtex data in the Bushveld complex is the DC train lines. So unfortunately, the deeper data was not able to be resolved because of all the noise from the DC train lines. So the crustal data was, however, very, very helpful, especially in the northern lobe. And in the paper with Carol Finn, I think it was Paul Bedrosian actually did a lot of the inversions on that to incorporate, at least in the upper crust, and in fact, fairly deep into the crust, the magnetotelluric information. So it was a sequential, if I remember correctly, it was a sequential inversion. So looking at the gravity and the MT sequentially, certainly not a integrated joint inversion, which at that time was really not fully developed. So I hope that answers your question. It's in that Northern Load paper by Carol Finn, which I think is the 2015 paper.
Thank you, Sue. It looks like there's no further questions here. I don't see. Oh, we've got one question, yes. Steph asks, when will the drilling happen for the ICDP project?
Oh, wow. Well, we actually got some exciting news the other day. It turns out the person who is helping us with making our budget came back with a budget estimate that was well within the amount of money we have raised. And so one of the issues is that the ICDP has to be convinced that we have raised enough money to go ahead and release the bulk of the money from the ICDP program. And you have to have an estimate of your budget, and it's always this kind of chicken and egg thing. And so with the recent estimate of the drilling cost, the ICDP has approved releasing the funding. So now we can really start pushing ahead. We're going to be during December starting to get contracts as best we can. Of course, with the December shutdown in South Africa, that's always a challenge getting things done. But we should be able to get at least some progress on the MOUs and contracts. And then we will probably be starting in February with release of funds and drilling in the new year, probably March, April. It'll be about a 3-month drilling program, and we hope to incorporate students in that, both as for training and to develop some local outreach programs also. So if you're interested in seeing a real live international drilling project, please contact us and get involved. Thanks, Steph.
Great, thanks for that, Sue. We're going to move on to the next speaker. And that is Joseph Maritinkole, who's here in person. And while he comes up, I'm just going to get his presentation up.
Okay, thank you very much. My name is Joseph Maritinkole, and I'm a student here in Wits doing my first year master's, and I'm under Prof. Ray's supervision and Dr. Vunganayimizi's supervision. The title of my talk is going to be Improving Automatic Local Earthquake Detection and Phase Picking Using a Deep Learning Algorithm. So that is the outline of my talk. I'm going to talk about the background and motivation, the aim, the data and the software, machine learning workflow, and my research progress. And the background and motivation, here I'm highlighting that I'm dealing with the most basic exercise in seismology, and that is earthquake detection and phase picking, which is needed for determining earthquake locations. And my research is motivated by the increasing seismological data that have been observed over the past years. And I'm saying automation routines have become an important tool to process this large data set. The automatic phase pickers exist, but lacks accuracy. And always human intervention is required to verify if indeed it's an event or not. And such phase pickers include the STALTA that I will talk about in my talk. And I am saying I am using artificial intelligence in the form of machine learning because it has demonstrated promise in overcoming the accuracy challenge with other traditional automatic pickers. And here I'm highlighting the weakness of the STALTA picker, which is the mostly and widely used method because of its simplicity. And the STALTA refers to the ratio of the short-term average over the long-term average. And in practice, the seismic energy of a seismic signal over a short-term window is compared to that of a long-term window. And in this case, the value that exists, the predefined threshold is going to be where the peak is going to be made. And in the diagram here, I'm showing the performance of the STALTA, but in very noisy data, it's not doing very well. You can see a lot of false peaks all over the signal, which can lead to association of peaks to form a fake event. And this is an example the peaks were associated to form a fake event. So in seismology, an event is a result of more than 3 stations associated together. So these peaks shown in the diagram, like I said, they were associated and they resulted in the fake event. Now you can see the need for human intervention for verification here. Or, like I said, that I'm proposing to use the artificial intelligence to possibly eliminate the human intervention. Here, I am showing the example of the large data set that I talked about. You can see the number of stations there, and these are not the only stations that we are using in seismology, and there are many, many more stations, and it's also good to note that the number of stations increase every day. And again, some stations are sampling at a very high sampling rate that gives out more data. And so you can imagine the manual processing dealing with all these traces every day. It's going to be a lot of work. And again, like I said, if this picker, like in this case, the picker that was used is the picker that I talked about, the STA, LTA, if it's always associated with the false peaks and detections, for example, when it is too noisy, obviously the human intervention is going to be required, and you can imagine the time that you are going to need. And the pictures here are extracted from the SciSCOM software, which uses the STA LTA picker, like I said, to perform real-time automatic phase picking. And the main aim of the study is to improve automatic earthquake detection and perform phase picking using machine learning algorithms through addressing the following objectives. By building a model using the labeled waveform data, and I'll show you what I mean by the labeled waveform data, and use it for simultaneous earthquake detection and phase picking. Comparing the developed machine learning model with other traditional automatic pickers, such as the one that I've mentioned already, the STA LTA picker. The study will answer the following questions, and the questions are: can machine learning algorithms increase the accuracy of phase picking and eliminate the need for human intervention? How effective are machine learning algorithms compared to the other traditional automatic pickers? So there's the data that I'm going to use, the data and the software. I'm going to use the data from the Botswana Seismological Network stations, the AfricaArray stations, the Global Telemeter Seismograph Network. And these are not the only stations that I'm going to use, but it's just that I'm going to give them priority because they have not been used in training any machine learning model. And the software that I'm using, I'm working with Python programming. So with this Python, I also work with the OpSpy, which works very well in the Python environment. I also work with the TensorFlow and PyTorch. And those are the programming tools for the machine learning. And the machine learning workflow, these are showing the steps that I'm going to use. So the first thing is to gather data X, and in my case is the 3 components waveforms from different stations. The labels OIE means the important information, which means you need to define your problem very well and know the most important information to use for your labels. Like, for example, in my case, I'm going to do the earthquake detection, and the signature of the earthquake there is very important. Is one of the useful information. And again, I'm going to perform the phase picking. Again, in the phase picking, the primaries, that means the primary window. It's very important. And again, the secondary, where I'm going to pick the secondary, it's again the important information. So the next step here is to choose the algorithm based on what you want to achieve. Like in my case, I'm going to use the CNN, or the convolutional neural network, which is inspired by the human visualization. And then I'll be training my model to look into the important parts that I just mentioned. So how does the model, this model learns? It learns through a loss function. So we keep on calculating the loss until it is reduced. And here again, I'm demonstrating that the model can learn any function. And in this case, the input is X, and it can map that into Y, or into give you the output Y. And those are examples of the below, this ones. They show the examples of functions. It can learn even complex functions. And the W0 and the W1 there, they show you the different weights that are going to be assigned. And the X there, it's the input data. So the X1, the X and the X2 can be the input data. And the W1, W0, W2 can be your weight. An example of a loss function there being the mean square error loss function. And the other examples of loss functions are the misfit function. Here I'm showing you the example of data that I'm going to use. Like here you can see the waveform data with the 3 components, with the labels A, B, C, and the labels there shows, the first one is for the detection part. It shows this, how an earthquake looks like. I use the term signature of an earthquake. B, it's showing the other important information where the primaries are going to be picked. C, it's showing where the model is going to focus when looking for the secondaries to make a secondary phase. And there's my progress with my research. So far I submitted the proposal, and all software has been installed and tested, and it's working fine. The data from the BSN stations is prepared. The OpSpice script code for downloading waveform data for events from Iris, it's already available, but I'm yet to install it. Revision of more literature to keep abreast with the latest methods is ongoing. I'm practicing using a software called the EQ Transformer, which performs simultaneous earthquake detection and phase picking. And you can see there that it makes a very nice pick, the P phase and the S phase in the diagram. I was applying it in one of our stations from the Botswana Seismological Network stations. And again, the offline playback script is ready to perform automatic picking using the STA-LTA picker. That is for comparison purposes. But right now, I'm more working with the software encoding. And the diagram again shows, this one, it shows the number of earthquakes. The stars there shows, the yellow stars shows a number of earthquakes that we picked, you can see these were the aftershocks to the 2017 Botswana earthquake. So there were so many aftershocks, and I used the EQ transformer to test if it can pick something, but it really picked very nice. And I've already compared, didn't show in this presentation. I've compared with the manual processed events, and they correlate very well. Thank you.
Thank you for that, Joseph. It was a very interesting talk. We've got a minute or two for questions. Anyone in the auditorium can come down and ask questions. Let's just stop sharing here. And then we can see in the chat here. Okay, so no questions so far in the chat. Please post questions if there are, and anyone can ask a question if they want to come down. Okay, looks like no questions.
All right, thank you.
Oh, we have a comment here, just from Ray. Really nice project. I hope that other African seismic networks will be able to use this work in the future. Thank you.
Oh yeah, thank you very much, Ray.
Okay, the next speaker is Alistair Sloan, who I believe is with us online, but he did send through a video for us to share, and
Maybe
then perhaps he can ask.
Sorry, maybe
Hi, Alistair, how are you?
I just say I would be happy to present the talk live. I wasn't sure exactly when it was going to be able to make it, and I see that you've scheduled me for 20 minutes, so my 10-minute talk might be a bit rushed, so I wouldn't mind the opportunity to go through it slightly slower.
That's great. That's great. Yeah, it's love for you to present live. So when you're ready, just share your screen and you can take it away.
Can somebody just confirm that they can see my screen currently?
Yes, we can see it from our side.
Okay, great. So I'm going to be talking about the results from a geophone deployment in southern Malawi. So this was funded by the NRF as well as the Prepare Africa project, which was from the EPSRC Research Council in the UK. The Prepare Africa is a much larger grant, which was done by people at the universities of Bristol and Cardiff, and this is just one small part of that. And I'd also like to acknowledge the Claude Lyon Foundation for their generous support of the postdocs, Vicky Stevens and Robert Muir as well. So the team from UCT were Vicky and Rob. They're currently in the Earth Observatory in Singapore, and Rob's taken up a lectureship at the University of the Free State since finishing this, as well as Guy Salomon, who's doing his PhD in Canada at University of Victoria. Patrick was our contact in Malawi and was very much a key part of doing this research. And Luke Wedmore from Bristol is the only member of the UK team who is actively involved, and he contributed a lot in terms of the geomorphological analysis that I'll briefly present. So I just want to start off. Oh, it is not letting me move on to the next slide. There we go. I just want to start off by explaining why I was so keen to be involved in this project. And it basically goes back to my PhD. My PhD supervisor, James Jackson, had written a paper about a particular fault scarp in southern Malawi, the Balila Matakataka fault back in 1997. I've always thought this was very interesting paper, a very interesting phenomenon, because it's a very unusual fault scarp if you look at it from the global point of view. It's 100 kilometers long. It appears to be very continuous. There are structural complexities. You can see that this isn't an entirely straight fault and that it very much is affected by the older geological structures within the area. But it had a very consistent scarp height. Originally, it was actually interpreted as probably failing, like the whole thing in a single event generating the scarp, which would have been a truly huge earthquake. more recent work, which was actually done through that Prepare project, which I mentioned earlier. So in particular, Matt Hodge published this paper in 2020, which had much higher resolution digital elevation models and allowed a much more detailed picture of the scarp to be built up. And one of the key findings from that is, rather than it being a single 14-meter high scarp, it actually consists of two separate surfaces with a terrace. So we're seeing signs that this is a composite scarp. It's formed in multiple earthquakes. But even so, they interpreted this as likely to be formed in two events, or the total height of the scarp could be built in two events. And if it ruptured the entire length, that still generates an absolutely massive earthquake, so high magnitude 7s. And even if some of these geological complexities that we see here caused it to be segmented, perhaps here, you would still be talking about an earthquake which was in the mid magnitude 7. So very large for a continental normal fault. There's been a recent paper, which I thought I would just highlight, by Neely and Stein, 2021, where they actually looked at continental normal faults in the global CMT catalog. So a global catalog of all the relatively large earthquakes going back over 50 or 60 years now. And they noted that when you look at these shallow continental normal faults, you see that the normal faults are here in pink, and you see that the maximum magnitude, the cutoff value, is actually in the very low magnitude 7s. And unlike strike slip and thrust earthquakes in the CMT catalog, which go up to about a magnitude 8, there seems to be this kind of restricted Mmax for normal faulting events. And obviously, this is something which potentially has quite important implications for seismic hazard, and maybe particularly in East Africa. So, if you believe that normal faults are only going to have a maximum of magnitude 7, as suggested by this figure here, then that will have implications for your probabilistic seismic hazard assessments. Why might this happen? Why this difference between normal earthquakes and strike slip and thrust earthquakes? Well, one suggestion is it might be related to the rheology. So as we all know, rocks are relatively weak in extension compared to compression. So that's illustrated by this Christmas tree diagram here. So you can see that the differential stresses on the extension side are smaller for an equivalent depth. This would be depth on this axis on the compressional side. So basically, extensional faults might be expected to support smaller stresses before failure, and that could contribute to limiting the maximum magnitude. So the rheology is potentially an important part of this question. And Malawi, along with the rest of East Africa, as I'm sure we all know, is quite interesting rheologically. So there's been a big debate in the literature. Largely one side may be suggesting that the entire crust is seismogenic in East Africa, going down 30 or 40 kilometers. But there's another point of view based on compilations like the one we see here by Yang and Chen in 2010, where you see this double peak in the frequency of earthquakes. And we can see Lake Malawi as one of the places that's gone into this compilation. And they suggest that the earthquakes are mainly in the shallow crust and in the deeper crust, or rather the shallow crust and then at the crust mantle boundary, and that they relate this to the kind of more mafic compositions, more olivine dominated compositions in the mantle, potentially allowing you to have more brittle deformation and more seismicity at these relatively deep values. Now, obviously, if you think the entire crust can be seismogenic, can be brittle, you would extend this line showing you brittle failure all the way down to the moho here. And so that would mean you would have a much larger area colored blue. And so the faults would be able to support much larger stresses. And that might therefore call into a question whether this model is applicable in East Africa, as well as many other places. Well, so instead of what we see in other places where most of these normal faults will have been taken from, which are kind of distributed rifting in places like the Basin and Range. So if we just go forward a bit to show you the area that we're looking. So this is the southern part of Lake Malawi. This red line here is showing you the Balila Matakataka fault. And then there's another fault here, the CNF, which we also talk about quite a bit in the paper, but you can see that these are on the western edge of the rift. You can see from the GPS vectors over here that the strain rate in southern Malawi is very low. The rift is only extending very slowly. And these colored dots just show you the depths of teleseismically investigated earthquakes from the literature. And you can see there is kind of broadly a few relatively shallow ones and a few relatively deep ones around 30 to 40 kilometers, one very deep down to 44 kilometers. So we don't actually have earthquakes immediately adjacent to the BMF, and the relatively few events we do don't necessarily capture the full range of the crustal thickness. So it's sort of a little bit difficult to know just based on these teleseismic events what the rheology looks like here. So this was the geometry of our deployment, 17 station network, 2 months of data. These are relatively low cost geophones with a 4.5 hertz natural frequency, 3 component geophones. We have a few more, but some of them failed to record, but this is the data that we had. And then this is just showing the results of the study. So the data was processed using SciSan, just using very standard techniques, hypercenter, VLS in order to constrain the velocity model. And we can see the colored points here are indicating the depths of the earthquakes that were picked up during this 2-month survey. And you can see that there are definitely these blue points over to the west, and you've got the hotter colors in the center of the basin. And that's indicating that the earthquakes there are getting deeper as you move towards the east. And you can see the location of the earthquakes relative to the fault scarps. So this is the BMF, this is the CMF over here in the east. We picked up some other earthquakes from the region, or maybe even some mining blasts. Those are obviously outside the network, so the accuracy of the relocations is limited. This is just what the cross-section through all of these events look like. So basically, we're taking this box and we're projecting the earthquakes onto a vertical plane with this orientation. And you can see that the microseismicity that we've recorded here does broadly form a dipping zone going from these 2 fault scarps at the surface down towards the center of the basin. There is this little cluster here, particularly in the northeast. These are, you could be interpreted as going where the fault on the eastern side of the basin would intersect with the main basin bounding fault from the west. They could also be related to aftershocks from some of those earlier larger earthquakes that we saw up in the northeast area on an earlier figure. And this shows the geometry of the fault relatively well. So these lines are showing a 45-degree dip. There's obviously some uncertainty based on the velocity model in particular, which we maybe estimate to be around 4 or 5 kilometers. And so that could slightly change the dip by moving these earthquakes up or down. And you can also see that we're not seeing a gap between 50 and 25 kilometers, which you might expect if the mid-crust were aseismic, if you had that kind of jelly sandwich model that we saw before. So we interpret this as being evidence for brittle behavior going all the way through the fault, and so that all the way through the crust, and so that there's a potentially seismogenic fault zone going all the way from the surface down to 30 to 35 kilometers. I wouldn't necessarily link these microseismicity particularly to either one of these 2 scarps that we see at the surface. And if I just go forward 1 slide, here we can see the topography of the area. This is the work which was done by Luke at Bristol. And you can see that there's a clear scarp here, but there's actually another clear scarp behind it further to the east, which was known as a fault, but wasn't necessarily recognized as an active fault, as having a fault scarp. But you can see in these profiles that there clearly is a fault scarp, which has significant offsets associated with it. And there is maybe just a hint that some of the areas where the scarp in the west is relatively low, the scarp in the height is relatively large. And so potentially what you're seeing is a larger fault zone at depth, which might be branching into one or the other of these scarps at the surface, depending on the individual rupture. And potentially rupture could either move back and forth from one to the other, which obviously has implications for the interpretation of the seismic hazard. So I think somebody's got their microphone on. Would you mind just turning it off? Thanks. And then just one final thing to point out, we have a few of these shallower earthquakes here, which are potentially associated with some topographic signatures of faulting within the center of the basin as well. So you do get earthquakes occurring on these intrabasinal faults too. Okay, so that is, I just want to quickly sum up. So the study defined the geometry of the structure relatively well. These are relatively low cost instruments, which could be used perhaps more easily by local institutions than the kind of broadband seismometer networks, which are very, very high cost to actually buy the equipment. In this case, although we don't have a major event on this particular fault scarp within the kind of instrumental historical period, there's still sufficient microseismicity in a 2-month period to provide useful information about the main structures. So this could be something that's useful to kind of address other places where we're not sure about the geometry of faulting. Generally speaking, I would say the results support the suggestion that the entire crustal thickness could fail in a single large event. And I don't think that this necessarily means we can say that upper magnitude from the CMT catalog that Neely and Stein suggested doesn't apply in this area, but it at least provides a reason why it may not, why the same rheological conditions that cause that MMAX might not apply in East Africa. And obviously, it's very important that as a community, we have a good idea of what the largest events that could occur in these areas actually are. And so I think that's something which is a useful area of future research. And finally, I mean, we're using this kind of method in other places which are maybe less seismically active, so more kind of stable regions to try and identify potentially active faults. So one project, we've just dug up the stations from a deployment north of Cape Town, and we're interested in looking for signs of seismic activity that may be kind of long-term aftershocks from events like the 1809 Milnerton earthquake, which is of course topical because it's close to Kuberg. And if you can use these kind of local deployments to pick out these structures, that would be useful in terms of informing seismic hazard analyses, particularly for these high value or high risk individual projects. So thanks very much. I'm happy to take any questions. That is the end of my presentation.
Great, thank you for that talk, Alistair. I'll ask anyone to come up in person who has any questions. But in the meantime, I see there are a couple of questions in the chat. So we have here from Ganai. I just wanted to find out how confident you are about the depth values you used in your study. What techniques did you use to calculate them?
So thank you for that question. So I think that there are always uncertainties in terms of the depth associated with the velocity model. So we used VelEst in order to try and kind of simultaneously locate the earthquakes and solve for a consistent velocity model. And we did compare those values. To things like published estimates of the VP to VS ratio. And the ones we got were kind of similar to, just a little bit lower than the ones which were from specific studies like receiver function studies in that area. But I would definitely acknowledge that there is some uncertainty. So I think probably what would happen is either you move everything slightly shallower or slightly deeper, and that could be by as much as 3, 4, 5 kilometers, particularly at the deeper end. So there is some uncertainty, but what we have is consistent with the other information within the area. So it's probably not totally wrong, if that makes sense.
Great, thanks. And there's one more question from Sue. There was some reflection seismic data collected in Lake Malawi. Was any of it deep enough to help map the faults?
Yep. So there is as he says, there is reflection data. And in some parts you can map the faults. I think particularly in the north, I mean, obviously we're a little bit south of the lake, so we don't have the seismic data in our particular field area. But as you go further north, there is. You can definitely pick up a large number of intrabasinal faults within that data where it's available. And you can also get an idea of the larger scale geometry, partly from the kind of varying thicknesses of the sedimentary strata within the lake. And that was used, so as I said, this is part of a much larger project. Within the Prepare project, they've created a new fault database, and that was in part informed by that reflection seismic data that you're referring to. So yeah, it is definitely useful. This is quite a good way of doing it where you're on land. You know, I mean, I think that within the lake you can get the seismic data, but there's much less available once you're in areas which are terrestrial.
Cool, thanks for that, Alistair. And we're glad you were able to present in person. So thank you for that.
Thanks very much. I hope.
Oh, we have one quick question.
Sure.
Sorry, one quick question from
Does
Steph.
it work? I'm trying. Hi, Alistair, Stephanie here. You might have covered it and I didn't hear. Why do you think that there's all the seismicity throughout the crust instead of just in like shallow and then at the moho? Is it because it's a actively forming young rift, or what are the thoughts?
So I think that it is probably, what's in the literature, and I probably subscribe to this view, is that in East Africa, you're looking at areas which might have lower crust, which is compositionally different from the kind of more rapidly deforming younger regions. So in particular, at some point in its history, you have had melt extracted from the lower crust, which would effectively kind of dehydrate it. So you have maybe a more kind of plagioclase dominated rheology. That means that you can support brittle behavior up to about 600 degrees C, as opposed to about 350 degrees C for kind of quartz dominated rheology, which is, let's say, wet, by which I mean that there's like water actually in solid solution within the minerals within the crust. So there's a paper by Tim Craig from 2011 in GGII where he addresses this. And I think there was actually also a more recent update in like 2021, something like that, Craig and Jackson, I think. So that has some more details on you know, that model. But I think, I mean, observationally, regardless of why you think it's happening, observationally, I think it is clear that in some places in East Africa, you do have earthquakes in the mid-crust. And one of the advantages of doing this kind of deployment is that you can maybe start to discriminate between whether it is this model where it's just that the whole crust is strong and so it can support faults which are cutting all the way through, or other alternative models which might relate earthquakes in the lowermost crust to perhaps fluid movement or melt intrusion and that kind of thing. So, you know, getting the geometry of the microseismicity might help us to be kind of sure of that interpretation.
Cool, thank you.
Thanks very much. Cool. Thank you very
Thanks,
much.
Alistair. I think, yeah, we've got no other questions, just one comment. Thank you for that. We'll be heading off for a tea break now. So those who are online, you can just put yourself on mute and grab a coffee, and the rest of us will take a break. Can we be back here by 11:25, please? Thank you, everyone. Welcome back, everyone. We're ready to move on to our next keynote speaker, which is Prof. Glenn Nwailer, and he'll be giving a talk on the application of machine learning in mineral resources. So I'm just going to pull up his presentation. Okay. Welcome, Glenn. You can take the seat.
Thanks, Michael. Morning, everyone, and thanks for joining us on our 15th annual meeting. So today's talk is mainly going to be quite informative for students and practitioners, and I will cover a number of themes and topics. Some of them are more relevant to academia, and some of them are more applicable to the industry. So how I'll go about this is I just want to first give you a bit of a scenario on what we will be focusing on. And if you're looking at the left-hand side here, you can see that it's a screenshot of a Netflix profile showing some Japanese anime. And this is where AI is highly developed and well applied. And what I'm trying to show you here is that with the new recommender systems that we find in much of these movie streaming services, if you watch one movie today, tomorrow they're going to send you another theme or a series of movies that shows something similar to what you have watched. And if you don't like a movie, you can simply skip and go to the next movie that you enjoy. However, as geoscientists, geophysicists, and geologists and geochemists, our job is slightly different because our decisions are quite expensive. So you cannot go to a place and drill a borehole, and if you're not happy with it, or do a seismic survey, and if you're not happy with it, and move to the next site, because that will cost you a number of millions. So the reason for showing you this is that there is a conception to say that AI is as simply as feeding in your data, getting some recommendations in terms of what you are looking for, and get an answer. And to show the complexity of this, I'm going to use this seismic profile that you see here on the right-hand side, which was created, and a total of about 412 geologists and geophysicists were asked to interpret this profile. And the main focus was to look at the tectonic setting, to look at the number of faults, and to also look at the horizons that may be of interest. So to do this, a pool of both well-experienced geoscientists and some of the juniors and graduates were asked to give an opinion on what they are looking at this profile. It is not surprising that regardless of the age of the person who have been working in the industry, the answers actually were completely different. So you can see out of the 412 people that were asked, a total of 21% of the participants interpreted the correct tectonic setting, only 21%. And about 23% of the people showed some sort of false positions and so forth. Not all of them were quite accurate. And the rest of the participants, including the more experienced one, measured as a number of years working in the industry or in academia or in whatever discipline that they profess in, they did not get all the answers correctly. And this actually shows us that as much as we have so much knowledge, so much data, we do need some sort of a machine-aided type of decision-making to avoid making such expensive decisions. And for this, there are a number of tools that are quite available. So unlike back in the days where we only had our hammer and paper to go to the field and map and gravity and magnetics, we now also have fancy tools that include 3D seismic surveys that we can consider, or EM surveys, among a number of new developments. But now the question is, if I'm looking for a particular deposit of some kind in the field, which tool do I start with? Do I start with seismics? Do I start with magnetics? Do I start collecting the data that exists geologically, which is quite qualitative? And this is the same question that many companies who are planning to implement AI or machine learning face, to say that where do we start and what do we do? So one of the most common approaches that have been practiced also by organization is to take all the available tools or available data, build a set of algorithms, because there are many people who can build complex algorithms, feed them in some sort of an AI engine of some kind, and expect some type of a solution. And I have decided to coin this model as a DNA business model. It's a do not adopt business model, because firstly, you are combining data that you shouldn't be combining. Secondly, this is going to cost you more because you're going to be hiring a lot of data scientists, mathematicians, computer scientists to come and do the job. And it means if your project doesn't succeed, you will say that AI or machine learning doesn't work. And lastly, if you apply AI, it shouldn't only be profit-driven, it should also be made to gain insight in your data. And how do we do this? There is a way that AI should be applied in reality in the industry, where we have all this number of tools. So we have to start with some domain expertise to look whether we have to acquire new data or we have to leverage the existing legacy data, or we also need to combine both these data sets to find out if there is any shortfalls in them. But most of the work that happens is not only on the data collection itself or data curation. There is more things that needs to be done. The first one is that we need to understand the details of data engineering. And this is a new discipline on its own that many of the geoscientists, some of them may not be aware of it, but companies are quite in need of this. Before, in the resource estimation side, we had people working as database scientists or specialists, but now it has changed because there are a number of things that you have to do. The first one is to explore the data in the context of the problem that needs to be solved. Data needs to be cleaned up for the purpose of exploration. Most of the time when we collect data, it's more in a gridded space, but we do also have data that is collected in an irregular grid, and we need to know how to deal with this, meaning we also need to normalize data that comes in different units and quantities. And then the last one, we may need to combine a number of disciplines, not only coming from geosciences, but maybe coming from physics and chemistry to understand more insights in our data. A typical example is that if we are dealing with any sort of geochemical anomaly, it means we need to understand which elemental ratios are going to give us results that are useful before we even start with a model. And this process needs to be followed by scaling of the data to make sure we are working on a unified data set. And it's only after this stage that we have to do some model selection. We have to train and evaluate the model, tuning and so forth. And most of the people end there and then straight go to deployment. And again, things tend to fail because there is more other steps that you need to go into before you deploy. So there is the issue of registration. But while trying to attempt to do any of these projects, there is the issue of data access and privacy. Not everyone is open to sharing data. There's also legal issues because some of the data has some legal bearing into them. There's also issues of ethics to say that, do I only use data from my mine site or from my study area, or I can also borrow some data from the neighboring mines, and what sort of agreements needs to be in place for that. And then there's issues of being biased. Most of the time, geoscientists, we tend to be quite biased to our data or to our algorithms, where we go with preconceived conclusions before we even go to the field. So this is another thing that can have a higher prohibition to start any machine learning project. And then the last two things is security and the trust, because much of the data that companies have generated or universities have generated may have some sort of issues or IP that should not be disclosed in public. And all these are realities that we have to face if we have to do any form of AI. But for us to do this before we even go to the case studies, I think it's worth to start with the philosophy of geoscience education, be it geophysics, geology, geochemistry, and any other form of flavor of geosciences that we have. And I have read many times there used to be someone who was quite active in geoscience education called Daniel Mikes, and he has actually written a number of papers on geoscience education. Speaking of that, of the fact that most of the geoscientists are taught statistics, mathematics, and coding as auxiliary credit courses. And it's only few ones that are coming from the physics stream, converting to geophysics, that get to enjoy mathematics. But it means they also have limited knowledge of the domain expertise of geology itself, because they do this as a one-year module of some kind. On the other hand, geologists spend their entire curriculum only doing mathematics and physics and so forth as part of their first year subjects. And by the time they complete their honors degrees, they have forgotten about most of this terminology or applications. But the challenge is that we have a new generation that was born between 1997 and 2012 called Generation Z, and there will be another one following that called Generation Alpha that will come in the years to come in the industry and universities. And these guys have a different view of what is geoscience education, because to them a degree doesn't matter much. It's all about whether there's a job prospect of some kind or there is application of this in terms of research. So I have also noticed, and this has been written in EGU and AAPG and AGU and a number of top geoscientific organizations, that this group of people find science quite extremely exciting these days. And they do want to study high-tech stuff such as biotech engineering, gene sequencing or gene editing, artificial intelligence, robotics, and quantum realms of computing and biology. But the trend is slightly different in geosciences, because we are seeing a life cycle of people who are saying that we can't continue studying geology or geophysics because we don't have a lot of job prospects. So enrollments have been declining across the specs, except in few disciplines. And some of the questions that we tend to view as trivial, because they are quite easy when you're looking at them on hindsight, but they are quite impactful on our design of the curriculum, is that should graduates be trained towards employers' needs and industry requirements? Is there a massive talent and training gap for a 4IR type of a world where many people will be working in? And do the learning outcomes of our different courses match the skill sets and training required for graduates to succeed in their professional practices? And in doing this, because I also do a lot of history reading and art, I came across a term which is called a spandrel. And a spandrel, many people have seen this in many of these medieval buildings and much of the old buildings, which is roughly a triangular space that people tend to see in many of the buildings. And it usually surrounds an arch on either side. And you have these open spaces. Back in the days, these were used as ornaments, decorating sites. So you will find if you go to churches, or you go to bridges and so forth, some of them have decorations. But if you look at them, they don't really serve any purpose. So they don't add any value, but you can use them for decorating things, but they don't give you solutions. So is the geoscience education in the same type of a realm where we have developed so many techniques, including new ones that many people are going to be speaking about in the geophysics side of things and in the geoscience side of things, where we used to have only XRFs and now we have lasers and microbeams and isotopic spectroscopies. But what have we achieved in terms of the scientific questions? So I will leave this as a question to say that is our geoscience education really outdated? Are we dealing with spandrels in our curriculum, or we have something like that is evolving over time? But my approach to the modern day geosciences and going forward, I believe that we are dealing with a lot of patterns, regardless of where you look. So if you look at the plant type of the system, you will notice whether you are looking at the tree branch or you are looking at the leaves themselves, we can see the same pattern. And the same thing can be mimicked in the human nervous system. And if you move to the river system, which reflects more of a geospatial natural system, what you will notice that it doesn't matter whether you are looking at the large scale catchment system or you are looking at a unified single river system, we can see the same patterns. And this actually tells us that in any form of a geoscience or geophysical system, we tend to have some sort of a spatial structure, which is quite useful for predictions and many things. And this is where I will spend a bit of time to say that much of the successes in science, be it in geosciences or in geophysics or in biological sciences, have been based on reductionism. And reductionism is more of a philosophical type of a principle in my view, because we tend to say that if we can have access to smaller scale particles to solve bigger problems, we can break it down into smaller units. And we as geoscientists are quite guilty of this, because we go and collect very tiny samples and we try to explain a bigger system. So This started a long time ago, where the discipline of biological sciences was developed, and we said we can reduce biological sciences into chemistry. And if we can explain chemistry, it means we can switch it down and reduce it. We can explain it using atomic physics. And if we understand atomic physics, it means we understand elemental particles. And from these specs, this is where computers were born. So we're now trying to use computers to explain all forms of systems. But I think the approach is no longer too valid nowadays, because if you're only looking at the tiny scale trying to explain bigger things, you run into more problems. And think of this case of you trying to explain the definition of a cat by only studying its limbs and so forth. There are other animals that have exactly the same limbs, so you may come up to wrong conclusions. So I think the direction is an integrated type of an approach, where we have to equip all geoscientists with some coding skills. We need to ensure that there is a well-embedded system of the domain expertise. And there's a new discipline that I would like to coin it, physical geodata sciences. So this is different from a typical commercial data sciences, where people are just dealing with commercial data. So I call it physical geodata science, because we incorporate a lot of spatial type of analysis. So in order to demonstrate what I have mentioned, I think it's only fair to give you some applicable case studies that many people will find interesting, both in academia and in the industry. So the first one, I'll be speaking of prospectivity mapping, which is a term that refers to a combination of all available geoscientific data to estimate the potential or the occurrence of a particular mineral deposit. So a prospectivity model is simply an integration function that relates to a set of features that we collect in the field, be it chemical or physical type of attributes. And we do this with the aim of saying, can we locate a deposit? There was a very nice talk earlier on by Professor Sue Webb that spoke of a bigger picture in order to discover more of these mineral deposits or to identify targets. So this case study that I'm going to give you today here speaks of that. So I'm going to start with a case study that we recently completed in the southern East Churchill province in Canada. And in here, we had to identify the potential of rare earth elements occurrences in a very complex type of a geological setting, where a number of geophysical surveys have been done and a high quality gridded geochemical data was collected. But the issue was, where is the rare earth element mineral deposit? Because we still need to analyze this. So this led us to review the existing techniques for mineral potential mapping. So on the left-hand side, you can see that we have the traditional multivariate geochemical prospectivity mapping that deals with compositional data, meaning that you put a spatial awareness on the data, and you need to make sure that your data sets sum up into one or sum into unity. And the general approach is to run some principal component analysis, and you combine it with manual interpretation. And with this, you are hoping to find some univariate anomalies of where you can find mineral deposits, and that's how you pin your targets. But this does not always work. We have developed our own new technique, which one of the papers was accepted just yesterday, and we'll be sending it off to many people who are more interested into this. And this actually takes care of the problem of dealing with compositional data or multiple variant data. And it leverages the power of machine learning, but not in terms of predictions, but in terms of analyzing residuals. And what I mean by this is that typically when we do any form of a regression type of analysis, the main focus tends to be the 45-degree line. And this is where we say that we have an excellent model that can predict this. But on our side, we have come up with an inversion of this, where we don't focus on the good predictions, but we are focusing on any scatter of the prediction that does not make sense. So then we collect all these data sets in terms of residuals, be it geophysical residuals that we have collected from seismic point cloud data or coming from geochemical data on multiple elements. And we create a new form of an algorithm that deals with residuals. So on the left-hand side, this is what we have produced using traditional method. So using this, you can see that there is no specific targets here. Almost each two-thirds of the area is almost a target. And if you look at the scale, this goes for hundreds of kilometers. It's not something quite small. So it's more of a regional type of a mapping. But using our algorithm, we have managed to combine the data set and highlight exactly where potential targets may be located. And this has been backed up by the physical data that people have tried to mine in these areas. So we have managed to narrow it down and show exactly where potential drilling or potential extra exploration can happen. The other study is a study that myself and Musa have completed recently, looking at the Black Reef deposit, and we are doing a lot of work. And to give a bit of context, the Black Reef is one of the youngest gold deposits in this country, actually the only youngest conglomerate-hosted gold deposit in the in South Africa at the moment. It sits just slightly above the Wits Basin. So what we're looking at here, this entire map here highlights all the Wits Basin gold fields which are located in this golden arc. And we are going to be looking at this West Rand and Carltonville goldfield. And here is a diagram that myself and Lena has produced to look at the basin wide scale. So you can see that the Black Reef is sitting just above in contact with other auriferous conglomerates. So what we have simply done was to look at the legacy seismic data. And the main purpose for this was to find out if there is some sort of a continuous geometry in the ore body of the Black Reef. And secondly, it was also to map out the structures, because there is also fears of saying some of these structures may have something to do with the genesis of the deposit, but they also pose a hazard when it comes to mining. So what we did was Musa worked on the seismics and he produced a very nice point cloud. And I took that point cloud and ran it in some sort of an algorithm, and we produced this ore body model that you see in here. And on top of that, we could locate, or we can predict, a number of geological structures that physically couldn't be mapped underground, or their continuity were not mapped properly. But on top of that, we can also pick up things such as dikes and so forth. So this is one of the outcomes that we have. But in addition to this, we also noticed that so since about 2011, I have been working with X-ray tomography. Those who are coming from the discipline of radiography will understand the principle of tomography. And what we simply did was to look at what is the best way to leverage what people have been using in the medical industry to scan bones, but in our case, to look at rocks. And what we have done was to subject a number of rock samples from the Black Reef and to see if we can detect any gold anomalies. And with this, we're looking at the linear attenuation coefficient and a different energy spectrum to say, can we even separate minerals using tomography and be able to mark them? And what you are looking at here is a virtual segmentation of a rock coming from the Black Reef that contains gold. The yellow type of particles, this is pyrite or sulfide mineralization, and the red portion means we can virtually strip off all the rock and study the 3D characteristics and the textures of the gold in the Black Reef. And this was one of the good things we have done. The other one is that for many people who are working in the hydrocarbons industry and so forth, they will attest to this problem that it's not easy to actually classify shale lithophases. The only lithophases that we tend to do is to distinguish between a sandstone and a shale, and it requires some more detailed expertise and explanation for you to be able to separate shale lithophases. What we have done was to look at a non-reservoir type of a shale coming from some of these old basins in the Archean, from the Barberton going into the Wits, and looking at some shales coming from Zimbabwe and other areas. And what we have done was to design an algorithm that can automatically detect lithophases of the shale. And the results that you are looking at here is covering a large spectrum of over 20 different lithophases of different rocks. And we're able to build an algorithm that can tell a number of lithophases of different shales, regardless of whether they are coming from gold-bearing deposits or coal-bearing formations, or even far much younger ones. And this is a good discovery that we have done that can be quite useful for those who are interested in reservoir modeling. So my last case study comes from a new deposit. This is quite an exciting deposit to work on, or an interesting deposit to work on. It's based somewhere in a place called Assen, just further north of Pretoria. And a couple of years ago, it was hailed as one of the youngest iron ore deposits, as much as mining has been taking place around this area in the Tabazimbi side. And as you know, the known iron ore mining in this country dates back to around 1200 AD. And you can see that we have a very long history of iron mining. But the complexity of this deposit is that it's highly weathered. So if you are working in this type of deposit, sometimes you can't tell which one is your iron ore body or which one is secondary non-mineralized deposits. And what you're looking at here, you can see that the dolerite dikes are the same as some of the banded iron formation or the hematite ore in here. So if you work in this type of deposit, you may find yourself mining a lot of waste that have no type of a bearing in terms of what you are looking at. What we have done was to run another set of algorithms, as you can see here, for automated rock classification on weathered surfaces. And on the far left-hand side, this is more of a benchmarking or blind type of a testing of known lithologies. And on the right-hand side is different algorithms that we have run, from logistic classifiers going to k-nearest neighbors and artificial neural networks. And we called with high level of precisions using decision tree-based assembly trees such as random forest and artificial neural networks and support vector machines predict exactly the stratigraphy and the rock type that we can find in the iron ore deposit. So in order to save a bit of time, I just want to leave many people with some sort of a take-home message to say that, firstly, I think it's time for most of us to embrace this new discipline that I call physical geodata sciences, because for this, it means it gives us a leverage, regardless of whether you're a geophysicist or you're a geologist, to run a lot of successful stories in artificial intelligence and data sciences. But this requires also a huge collaboration between the industry to supply the data, the government to assist us with funding, and together with the industry and academia to allow transition into these new curriculums that can do this. And I envision the future being divided into two ways. One, which is what I call the dry laboratory. So for those who have been to the Vet School of Geosciences, you'll notice that we do have the Seismic Research Center. So I'll call that our dry lab. And we also have a large earth lab or earth science lab here at VETS that deals with more of wet chemistry and so forth. And I think it's about time we take the two together in order to enjoy the benefits of fourth industrial revolution, requirements of a workplace, and to ensure that we benefit from all our data. And with this, I would like to thank everyone for joining us and enjoy cognitive learning in geosciences.
Thank you for that, Glenn. Yeah, we have some minutes for some questions. If there are any questions in person here or online. Okay, there's a question here from Prof. Ray Durheim. What changes, if any, should we make to curricula in the Wits School of Geosciences?
Very nice question, or interesting question, Ray. I think for us is mainly the incorporation of some numerical methods in the geology curriculum, whereas in the geophysics curriculum is to ensure that we don't just streamline it to a couple of months of learning basic geosciences, but there is actually details of some of the main components of geology, because this becomes a limiting factor. If you have a geologist who have to go and deal with models, but have no clue or have limited knowledge of mathematical or statistical knowledge, and whereas this is more of a common trend nowadays in the industry, whereas on the other side in geophysics, we have people who are very well clued up in terms of mathematics and physics, but their knowledge in some of the geology or fundamental geology discipline expertise are limited. So it's more of an integration of the two. I think we have sufficient people to do so.
Great. There's another question here from Sianda Mgandi. Why do we have so many geoscience graduates unemployed? Geoscience graduates unemployment.
I think this is a complex question, but I'll try to simplify it based on what I have presented. But of course, this goes beyond just what I have just presented here. I do feel that most of our graduates are only trained at skills that has to do with traditional approaches to geosciences. And with this, some of them are no longer even enrolling for this, not because of lack of jobs, but they know that by the time they leave the university, they'll be well versed in terms of mapping skills, but they are not much computer literate to do anything beyond the mines or environmental consulting and so forth. So I think this also has to do with some skills shortage in terms of numbers, in terms of coding and so forth, because if they had sufficient skills, most of them will work in investment banks, but you can only count the number of geologists or geophysicists that end up taking jobs in investment banks or advisory services because of limited skills and experience in these disciplines.
Okay, great. No more questions on the chat. I see no questions in person. Thank you, Glenn. Thank you for a very thought-provoking talk.
Thank you.
Okay, moving on with the program. The next speaker is Sianda Mgani, who's online, I believe. So Sianda, I see you've got your camera on. If you can share your screen and then take it away when you're ready.
Okay, thank you very much. Thank you very much. Is it morning? Good day to everyone. My name is Sianda Mgani. Glenn, I think this was a great presentation because these are some of the social and soft issues that we need to address if we are to promote geoscience as a profession of the future. We acknowledge that there are problems that still persist in our society that require geoscience technical expertise. For instance, our geoscience also, Glenn, maybe it might have been extremely focused on mining and exploration rather than engineering side of things. I mean, there is a recovery plan where it's focused on infrastructure and perhaps geoscience expertise to do some hazard seismic assessments, to do some ground evaluation, to look at integrated approach. I mean, geoscience is applicable for groundwater, is applicable for mining, but also if one to understand what is the best use of land, geoscience is also applicable. So perhaps we need to reinvent ourselves as a profession to solve general societal needs. So today, it's interesting, Glenn, that you talk about investment banking. I found when I started, when I was doing a graduate program in one of the investment boutique companies that looked at listed equities. There were, the guy who was our boss was a geophysicist, and out of 5 people who were in that graduate program, 2 were geophysicists. I find it quite interesting with your observations because they are quite true. So I'm going to be giving a talk here on the effects of gouge layer and rupture propagation along underground shear fractures. So basically, I'll be looking at underground shear fractures that form in deep underground mines as you mine below surface. So this is the outline of my talk. So I was involved, unfortunately, I was involved in a ICDP DSISE project, which was targeting to drill in deep mines, really to understand the science and the physics of earthquakes that are occurring below surface, and see if that could be understood in relation to tectonic earthquakes that are occurring in your plate tectonic boundaries and also your subduction zones in places like Japan. So this collaboration included working with Japan, India, US, Switzerland, and several partners. And maybe let me take this opportunity to say, may TC's soul rest in peace, who was a key component in this DSISE project. Maybe if we can just take a second, a moment of silence. Thank you. So these targets, we targeted Savuga, 3 mines, Savuga, which we couldn't drill because it was eventually closed. We targeted Moab Kutong and Kukfo mine, and also Kukfo mine, we just made it because in fact, while we were drilling, the mine was actually closed. So we're getting special permission. So this for me, it's a privilege because some will not experience some of these deep mines, at least in the gold, because when we're doing these projects, some of these mines were undergoing closure, and you know that there are very few now opened deep gold mines. So we successfully drilled holes at Moab Kutong and Kukfo, and we had a budget of $1 million US dollars. Now, these targets are situated in the Wits Basin. I think our previous speakers has touched on the Wits Basin quite extensively. So at Kukfo mine, we looked at the remnant shaft pillar. So they would have been mined many years ago, and the mine would have undergone a closure and reopening. And so we had to, so the Spaniard, we had to mine the rim pillar, which was left. So we needed to understand from our side the fractures that are forming ahead of the stope, and also the stress conditions that are occurring in these remnant shaft pillars. You'll know that they will have large concentration of stresses in these remnant shaft pillars, and therefore they are prone to seismic events. Then you have fatalities and injuries. In fact, even now, one of the largest contributors in fatalities in the mines is fall of ground and seismicity. So it still persists as a serious challenge in the mines. Now, so I keep on talking about these brittle shear fractures that are occurring ahead of the stope. So if you see, this will constitute a stope, this hole, and then this will be your mining direction, this will be your support, and then you have these large fractures occurring ahead of the stope and around the stope. And of course, these are prone to emitting a 1 to 4 a large earthquake, and sometimes they don't emit. So you have shear fractures and then extension fractures that are occurring almost at vertical or perpendicular, I would say, yeah, vertical. Now, of course, one thing that I think of critical importance that we have realized in line with what Glenn was talking about is our investigation of or sampling of a small area and then making deductions on a larger scale. So what we have done, actually, interestingly, in this project is as if we caucused with Glenn. We looked at micro, macro, and kilometer scale at our my PhD. So we looked at what are these small controls, what are macro controls, and then what are the larger scale controls, so that we see a complete picture to address the same problem that Glenn, a reductionist theory, was alluding to. So we've conducted some underground mapping. With previously there was a project called Subtrace Projects. So that project actually monitored these acoustic emissions or these microseismicity that are occurring ahead of the stope. And we could clearly delineate them. We're looking at magnitude as small as -1. That would be your centimeter deformations. So we could, in high resolution, delineate these shear fractures. And of course, we drilled into these shear fractures using a triple tube a drilling a technique to make sure that we recover some of these rock, and we study it in detail at micro level. And of course, we would have observed them at a macro level as well and monitored using acoustic emissions. So this is the highly fractured core that was drilled ahead of the stope to sample these shear fractures. And of course, these shear fractures would have been delineated using these high resolution acoustic images. So we analyzed this core with Harry and several partners in ICDP DSISE projects, including colleagues from Japan. So we could identify a couple of these shear fractures, and we could link them or correlate them with some of them the geophysical borehole logging that we conducted. So we intercepted or analyzed 4 different shear fractures that were occurring ahead of the stope. And in those areas where it was recovered, these fractures, they were associated with gouge samples, as you can see shown here in the picture. So we analyzed the particle distribution of this gouge. We also analyzed the particle distribution of an artificial gouge because we could not sample enough gouge because we wanted to test it in Japan. So we then crushed some rocks and recreated the gouge that we're observing in these shear fractures so that we could conduct some tests to arrive at a proper statistical position. So we measured the composition of these gouge samples, and then we prepared a friction experiment. So why did we want to conduct friction experiments? Because we understood that the static part of these fractures are well understood in terms of how they form, where they form, the direction in which they form, but none of a dynamic approach has been pursued, at least to our knowledge. So we prepared samples to conduct friction experiments. So we wanted to understand what controls the dynamic rupture propagation of these shear fractures that are occurring ahead of the stope, because some do not actually undergo through unstable rupture propagation and some do. So I wanted to understand whether these factors are controlled by the geometry of pre-existing fractures, they are controlled by a gouge, they are controlled by frictional heating. What really controls this unstable rupture propagation that actually results into fatalities underground? So we conducted 2 sets of experiments. We conducted high to low velocity experiments, but the first experiments, they had a gouge layer in between. So we inserted a gouge layer in between 2 rock samples, as you can see, and then we enclosed it with a Teflon sleeve so that it does not escape. And then the second part of experiments, we actually conducted friction experiments without necessarily an intervening gouge layer. So it will be a rock on rock layer. And of course, part of what you need to ensure when you're conducting these experiments is that you get make sure that they are extremely parallel, these 2 rock samples, so that you do not create what I will call uneven contacts between 2 surfaces. So we got the results, and we found a very interesting result. Firstly, what we could observe is that with this gouge, when you conduct these experiments with gouge interface in between, you actually delay the unstable rupture propagation. So in simple terms, I'm saying that the unstable rupture propagation, when you have a gouge in between the sliding surfaces, it tends to delay that unstable propagation. Now, what we observed with 2 blocks with no gouge is that firstly, it actually weakens at a far lower slip velocities compared to the ones with a gouge. So for us, this was quite interesting because even though you had 2 similar slip velocities and pressures, you still find the experiments with no gouge weakening very fast. So what it tells us here is that depending on the amount of gouge that you have in between the two sliding surfaces, that has an impact on your unstable rupture propagation, and of course that has an implication on the safety and vitalities in the mines. So when we're trying to understand what drives these samples that have no gouge, what drives them to slip quicker at lower slip velocities, we then took data from other studies that were linked to subduction zones and tectonic studies. And we saw that this was not a unique pattern as it plots. You see our rock on rock is purple. It plots well within some of the observed studies in other parts of the world. And then you see with gouge, they form a little bit higher in terms of frictional strength, and of course, the delay in weakening. So there are a couple of things that we took out from these studies. Firstly, we know that the rock-on-rock experiments, they weakened at a very slip velocity. Now, we wanted to understand, and of course, at shorter weakening distance. So it took them less displacement, and it weakened faster at lower slip velocity. In other words, we don't have to have high slip velocities because also if you have high slip velocities, they control the weakening mechanism. So that is long established. So we looked at other factors beyond just slip weakening velocity. So in this case, we actually were amazed that why would you have such weakening at slow slip velocities? And of course, you have very small slip weakening displacements compared to gouge experiments. And of course, we then looked at the impacts of a frictional heating or flash heating in this case. We understood that quartz has a high indentation strength. Now, what it does when you have two sliding surfaces, you create more frictional heat in between those sliding surfaces. And then you induce what we call flash heating. And flash heating then drive this low velocity slipping. And we observed that, but that was actually delayed when you have your gouge in between the layers. So we wanted to understand why is that a slip weakening delayed when you have a gouge. What we found is that when you have a gouge, you have many contacts compared to when you do not have a gouge. And what it does is that it actually slows your average velocity. When it slows your average velocity, it then you need much more a movement of velocity for you to push your velocity high. So you then delay your weakening process in order for you to activate your slip, your unstable rupture propagation or your slip. Now, what we learned from this study is that, firstly, high velocity does control your slip weakening, and we see that the similar behavior both from underground mines and with tectonic results. But what is more remarkable about this is that even though at low slip velocities you have similar velocities and pressure, when you have when you have your rupture surface with no a significant gouge, you are likely to have your a slip of unstable rupture propagation and therefore causing much more fatalities in the underground mines. So in this case, we then conclude that perhaps the gouge generation and the presence of gouge does influence the unstable rupture propagation. And we think that if you have those and you have maybe a higher gauge generation, you are probably going to delay the slip weakening, and in some instances reduce the likelihood of unstable rupture propagation, which ends up in large damaging seismic events in underground mines. And of course, what is the future work? It will be interesting to understand what is the gouge thickness in terms of the threshold that delays the slip weakening behavior. And the last time I conducted these experiments in Japan, and I left some of the samples, and our Dr. Akito called me to say, can they use my samples to investigate this first question of what is the gouge thickness? Because also for them, from the subduction zone point of view, they were quite intrigued with these findings, and they wanted to understand more. So that's how Japan and South Africa collaborate when it comes to seismology. Now, also what was of interest to us is to examine the displacement with true conditions of South African mines. So if we could increase the pressures that we apply in these experiments, we want to see exactly what would be the displacement of these shear fractures, and of course compare them to our observations in South African deep mines. And of course, if we can monitor and measure what is the mechanisms that controls this weakening process, and then if we can as well observe if there are any evidence of slip localization. Thank you very much.
Thank you for that, Sianda. I'm afraid we don't have much time for questions. There are a couple of questions in the chat, but perhaps you could take some time to answer them. And there is a comment from Ray that I thought would be nice to read. It says, congratulations on your PhD graduation on 17 December. Looking forward to saluting you as Dr. Mgadi. So I think we can join Ray in that congratulations. The next speaker is Kenneth. So Sianda, if you wouldn't mind stopping your screen sharing, and then we can bring on Kenneth, who's online.
Oh, thanks.
I'm not sure if you can see my screen, Michael.
Hi, Kenneth. Yes, we can see it.
Okay.
Yeah, take it away.
Good day, everyone. So today I'll be giving a presentation on some of the work that we've done at the Maseve mine, which is seismic solutions utilizing existing in-mine infrastructures for mineral exploration, which is a case study from the Maseve mine, as I've mentioned. So my presentation outline is as follows. I'll go through my background and objectives, take the general geology, do data acquisition, go to processing and results, and show you some of the concluding remarks. So in 2020, we conducted seismic experiments at the Maseve Platinum Mine in the Bushveld complex. And these seismic experiments were part of the Advanced Ore Body Knowledge Program, looking into developing technologies that will be used to obtain information ahead of the mine phase. And the main objective of this study is to characterize geological structures using different seismic data acquisition techniques in deep platinum mines, and also to substantiate the accuracy and cost effectiveness of using seismic geophysical techniques for ore body delineation. So the studies were conducted at the Maseve mine, which is located on the western limb of the Bushveld complex in the Boshuk area. And several mines at this location are currently in operation extracting the PGE, chromium, and vanadium deposits. The economic horizons are found in the mafic to ultra-mafic cumulate rocks of the Bushveld complex, and the two major horizons, which are the Marinsky Reef and the UG2, are mined at average depth of about 500 meters below the surface, with the UG2 occurring about 15 to 400 meters below the Marinsky Reef. So to get a better understanding of the site's reflectivity response and the origin of our reflections in our acquired data, we calculated synthetic seismograms using a borehole provided by the mine. And we started by collecting physical property measurements, which is the seismic velocity and density values of the hanging wall and the foot wall at the Maseve mine. The borehole that was provided reached depth of about 578 meters, and it has intersected the two reefs of interest, which is the Marinsky Reef and the UG2. It intersected the Marinsky Reef at about 515 meters, and the UG2 was at about 571 meters, just at the end of the borehole. Then, when we were conducting this synthetic seismogram, we used a Rika wavelet with a dominant frequency of about 130 hertz and a sampling rate of 0.25 milliseconds. The Marinsky Reef and the UG2 are too thin, which are about 1 meter or below in thickness. They are too thin to be directly resolved, while the acoustic impedance contrast of the hanging wall and the foot wall is large enough to actually provide us some significant reflection response. The reflections of the UG2 are more prominent as its acoustic impedance contrast with the host rock is actually higher, as you can see it on. I'm gonna try to get a point. As you can see it on the synthetic seismogram. We used the information obtained from the borehole and geological reports from the mine to build a 2D acoustic model. And this 2D acoustic finite difference modeling was conducted to investigate the seismic reflectivity of the mineralization and also constrain the seismic interpretations. The thickness of the Marinsky Reef in the study area, as I've mentioned, is below 1 meter. For this study area, it was 0.63 meters, while that of the UG2 is 0.84 meters, with an average dip of 7 degrees. The area is prone to faulting and dikes, dolerite dikes that cross-cut the mineralization. But as you can see on the model that we have conducted, the dike does not extend to the bottom of the model, as there is no geological information that constrain it in terms of does it cross-cut the UG2, does it go to greater depth? And this bringing to us to extend the objectives of the project and follow on to investigate the extension of the dike. Therefore, that is why we included a dike and some faulting on our model. Modeling in the tunnel is conducted with the assumption that the tunnel floor is actually the surface. The synthetic parameters of the model were kept the same as the acquisition parameters of the collected data. We acquired multiple seismic lines on surface and underground at the Maseve mine, and the in-mine survey consisted of 7 experimental profiles that were acquired in the exploration tunnels, covering about 600 meters over the known platinum deposits and geological structures. But in this study, we only focus on the 3 of the underground experimental profiles, which is the P5, P6, and P7. The data was acquired using a 5 kg sledgehammer, 4.5 hertz geophones attached on a seismic lens streamer, which those are vertical geophones. We had a 5-meter shot and receiver spacing. And to improve the signal to noise ratio, we had 4 hammer shots at 1 shot location. And the lens streamer was inspected to ensure that the plates are well coupled with the ground. And now to get accurate in-mine coordinates of the receiver and sources, we had to extrapolate the using the coordinates obtained from the mine packs. Now, seismic profiles P5, P6, and P7 covered the bottom part of the incline tunnel. And this is a few meters above the dipping Marinsky Reef and the UG2. The data were of good quality with few noisy traces due to low coupling of the lens streamer in the muddy ground of the tunnels. The first breaks were clearly distinguishable along the entire profiles, which is the shot gather shown in the middle here, while the first shot gather is the synthetic shot gather produced from the model. And you can clearly see R2 on the synthetic model, which corresponds with the UG2 reflection. So some of the reflections in some of the shot gathers, that we had were masked by the noise, the mine-induced noise. So the first step that we did was to then fix the geometry of the seismic profiles and pick the first breaks that will be used to produce seismic tomograms and also aid us with the interpretation of the data to about 30 meters to 40 meters. We then applied statics using only the short wavelength component and applied some filters to constrain the data within the source energy and remove the mine-generated noise. We stacked the data and went on to do a 2D Kirchhoff migration. The seismic tomograms show that the top layer has velocities ranging between 2,300 to 3,400 meters per second and an average thickness of about 3 meters. And the hard rock is observed at depth of about 10 meters with velocities ranging between 4,500 to 6,700 meters per second. The velocity of the top layer corresponds to the loose rocks and mud regions in the mine, while the hard rock velocities match the velocities of the footwall rocks, which are the norites and anorthosites. Merging of these 3 segments, which is P5, P6, and P7, have resulted in areas of low ray coverage. As you can see it on the diagram, as you are about at 120 meters, you can see there is low ray coverage in those regions. The seismic tomograms exhibit areas of low velocities, and these areas are marked with the dashed lines and can be interpreted as fractures that are actually visible in the tunnel floor and the face. And we can also see high velocity zones outcropping at about 70 meters, which we can also see the general structure of the hard rock, which is dipping, which is a bit lower on the left side of the image. As you move along the tunnel to P7, the fractures are persistent, which we've also seen that in the tunnel, the fractures as you move ahead are quite persistent, and we are expecting to cross-cut a dolerite dike in this region. The unmigrated stack section and the process shot gather are shown here, and the reflections appear to be cross-cut along the line due to the data being collected as 3 separate profiles, as I've mentioned. Therefore, merging these lines into one profile resulted in a low CDP fault in the areas where we have matched them. But R1 is associated with possible deep mineralization below the UG2, while R2 is associated with the UG2. The depth stack section honors lateral variations of velocity, and the reflections are more continuous compared to the stack section in the time domain. Now, looking at the reflections, the shallow reflection R2 occurring at about 70 meters corresponds to the depth of the UG2 on borehole 1. The seismic section resolve reflections below 30 meters. Therefore, the Marinsky Reef cannot be easily identified as it falls within this region, the 30 meter that cannot be resolved with the seismic sections. The first 30 meter is resolved by the seismic tomograms showing high velocity rocks starting at about 6 to 10 meters. The two reefs are closer at the edges as the UG2 creates a syncline structure, and the two mineralizations cannot be directly resolved as the vertical resolution is limited to an average of 25 meters, while the detection limit goes to about 7 meters. The geological model shows the presence of a dike, as you can see with the green, the presence of the dike and faults in the study area. The dike observed on the geological model was about 3 meters in thickness, which is below the seismic resolution limit. Therefore, the dike was not resolved in this section. The displacements of the reflections can be linked to the faults. However, the displacements observed on the data is likely to be due to the low fold areas, which calls for us to collect this data and in a continuous manner rather than collecting separate profiles. Therefore, the interpretation of the faults is quite inconclusive. In looking at the conclusions, the integration of 2D modeling, borehole data, and geological information assisted in the interpretation of the seismic data. The UG2 is imaged with confidence using the contact between the hanging wall and the foot wall. And additionally, there are other reflections that can be attributed to deeper mineralizations below the UG2. And the seismic data clearly shows mineralizations and illustrates the potential for this study to image the targets. This study shows how high resolution in-mine reflection seismic data can be used for development. It opens the possibilities of using reflection seismics for exploration in difficult mining environments. And the work that we have conducted has been accepted for publication in the leading edge and should be available soon. Thank you. Any questions? I see there is a question by Prof. Ray, which says, I'm not sure if anyone can still hear me.
Yes, we can hear you.
Oh, okay. I'm not sure if Michael is still around, but I'll just answer the question from Prof. Ray. The question says, did you use the results of the refraction tomogram studies, the thickness and velocity of the low velocity layers to make static corrections when you did the reflection seismic Yes, Prof. We did use the results from the peaks that we have gotten to do static corrections when we were doing reflection seismic processing. And then the second question says, how do the variation in fold affect the depth migrated image? I'm not sure if I understand the question, but I can answer it after. I can actually type in the answer, or you can ask me, you can rephrase the question for me, Prof.
Hi, Kenneth. Sorry about that. We were muted this side. I was just saying that we've decided to move Nandipa's slot to a later stage, so we do have time for questions, and in the meantime, Reese can maybe get ready. But Kenneth, I have maybe a comment on which is related to Ray's second question. When you look at your stack section, the amplitudes are consistent across the different fold variations. So I imagine you did like a post-stack amplitude recovery. Is that correct?
Yes.
It might be an idea to remove that amplitude gain and look at those different amplitude bands, because where you'll have a high fold, then you have a higher confidence, or you'll be able to see higher amplitude reflections, and then it will boost your interpretation.
Oh, yeah.
Yeah, Michael.
Yeah, I see no more questions. Yes,
can I
Ray.
carry on? Yeah, I think you've got the essence of what I'm saying there, because of course, where you've got a low fold, let's say over here, I see the image around, say, CDP 150, you then expect to have a lower signal to noise ratio. And so even if you just boost the, let's the amplitude, you see you've got folds up to 25 fold at the best, around 120. So you just expect about a 5 times better signal to noise ratio where you've got a high fold than where you've got a low fold. And so if you just boost all the, say normalize all the amplitudes, you might be boosting noise rather than similar signal. And so you could end up interpreting, let's say, changes in the strength of your reflectivity as, let's say, as a structure rather than an acquisition issue. So that's, I guess, what I'm trying to say.
Thanks, Prof.
We have another question or comment from Musa Manzi here. Do you want to use your?
Yes, thanks, Chair. Thanks, Kenneth, for a lovely talk. Of course, difficult conditions underground. It's not always easy to acquire seismic surveys. Just a comment. When the survey was done, actually, there was no prior geological information like where the dikes were located, hence the different profiles. But then we got the data from the mine, the geological maps, as well as the location of the dikes and fractures in the fault. So we going back to the mine to actually now do, we're gonna overlap the profiles at least by 50% so that we ensure that where we match the profiles, actually we've got good coverage in areas that have low fold currently, which means that I fully agree with Ray. I don't think you should play around with the amplitude there, because then you'll be boosting noise. And we know that where there's low fold, basically we have no data there. So I think you should leave it the way it is. But then when we go back, then we overlap the profiles in those areas to maximum the fold. Coincidentally, we found that actually the fold that has been mapped pretty well in the mine is actually located in the area where one of the profiles ended. So we actually missed the fold. So now, because now we have the information, so we'll overlap those and make sure that we maximum the fold in the areas that have dikes and faulting. Thank you.
Thanks, Musa. Okay, I think that's all the questions we have now. Kenneth, if I can ask you to unshare your screen. And then if Reese is online, could he share his? I don't see Reese here. There you go.
Hello, everyone.
Hi, Reese. Thank you for joining us virtually. It's great to have you. Yeah, please take it away.
Always a pleasure. Thank you for the opportunity to address the audience at AfricaArray today. I'm glad we were able to come together, even though it was a little bit delayed. I hope I'm not preaching to the converted or only to the converted. I'm just going to give a very brief overview of the South African Geophysical Association, a little bit about where we come from, what our activities are, and a call for further participation. So once again, thank you. You can see some of the AfricaArray sponsors presenting at a South African Geophysical Association talk, Saga talk, in the center there with Ray and Hiroshi flying the flag. So a bit of background, South African Geophysical Association stems from the mid-1970s, principally sponsored by a number of major mining houses in South Africa at the time. Since has grown into a few different branches. We've got local subcommittees in both Johannesburg and in the Western Cape at present. Just a word to our corporate members, Anglo-American and Digital Survey. Sorry, I'm not clicking on the right screen. Next. We do have collaboration agreements in place, which are quite pivotal to the functioning of our association. We're quite a small association at the present time, but leverage, as I mentioned, collaboration agreements with the likes of the entities you see on your screen. Recently, we've co-hosted or collaborated with the Society of Exploration Geophysicists in the Middle East to run a virtual event, but locally in person here in Johannesburg, which was quite well attended and something we intend to capitalize on and do more of in the future. Just so you're aware, we do have collaboration agreements with the likes of local entities like GSSA and SIMM as well. And that gives our members the ability to leverage membership rates to GSSA and SIMM events and on the purchasing of a number of the resources like their books, etc. So just onto the vision and mission of SAGA. As a general vision, we look to positively impact society through the application of geophysics. We are geophysics-centric. It's the preferred forum for equal opportunity engagement and inclusive collaboration. And we want SAGA to be the home to geophysicists across all industries, not just mining and oil and gas. Our mission, SAGA was founded in 1977 to foster and encourage the development of geophysics in South Africa. Subsequently, I think we've got membership not just from South Africa, not just from Southern Africa, but much further afield. So Europe, North America, Australia are quite strong membership locales for the Geophysical Association. The general structure of the association, we've got our membership. We've got different membership categories and for different regions. We've got an executive committee, which is comprised of officers of the association and executive committee members. Aside from that, we also have directors of the association. It is registered as a not-for-profit or non-profit company. So we are able to accept donations, for example, now formally. We have formulated various subcommittees that are represented on the executive committee. I think I've got a slide that will touch on that quite briefly. And then recently we've established a panel of experts. And this panel has been drawn from experts across a variety of industries and geographies, so not restricted to South Africa at all. And the intention there is for the panel of experts to become an advisory for the executive committee as and when required. In terms of functional subcommittees, we've got a finance, legal, and secretariats. We've got a technical excellence focused committee. We've got a student subcommittee, which needs to be more strongly represented at more of our institutions across the region. We have a marketing, communications, and social media subcommittee, education and training, IT to establish all the infrastructure we require, and one of the major activities that the association conducts from time to time, generally biennially, but COVID's thrown a bit of a spanner in that works, is the SAGA conference. Then we also have a branch in Johannesburg and a branch in the Western Cape in Cape Town. But we are looking to extend that into more regions. So through collaboration with local committees, local geological societies, etc. And then off to the side, you can see the panel of experts. So as I mentioned, we run this biennial conference and exhibition. It really is the highlight of the geophysical fraternity in the region and well attended by multinational representatives. The last one being in Durban in 2019. We were supposed to just have had the 2021 conference. Unfortunately, with the COVID lockdowns, that's been delayed until next year, but we're all expecting news on that with bated breath. You can see on the right-hand side here the history of geophysics in Southern Africa. It's called HOG. It's a book that's been published in collaboration with the Geophysical Association, and it is available for purchase through SAGA. We've launched mentorship programs in the past, latest formalized in 2017. The mentorship program essentially looks to pair students with mentors. It has recently been extended not just to be students with mentors, but early career graduates also with more senior mentors. And the idea there is just a 1-year collaboration between a student and a mentor. It has been recently in collaboration with a program called Bridge the Gap that I'm sure most of you are aware of. The Bridge the Gap in the past year has been extremely successful. I don't have the numbers on hand at the moment, but I know we've had a number of really useful collaborations between mentors and mentees. In terms of discussions that are facilitated, I imagine a number of you would have been quite au fait with a number of the discussions that have been on social media recently around seismic surveys off the South African coast, around the exploitation of non-renewable resources. South Africa does use a lot of coal, which is quite a large carbon contributor. There's many different opinions that have been put forward, and part of SAGA's role, I think, in society is to coordinate and participate in these discussions, not necessarily as a primary contributor, but to ensure that all the voices are heard and that there's a platform for that. Up in the top right-hand corner, you can see an image of the Lily mine after the Lily mine disaster, and something that SAGA was involved in at that stage, and which I would like to see carried forward, is collaboration with entities such as Mine Rescue South Africa to form a point of contact in emergency situations, not necessarily just on mines, but anywhere where geophysical methods could be used in emergency situations. At the time, we were quite focused on finding the individuals that subsequently lost their lives in the Lily mine disaster. But I think there's a much broader discussion to be had around how geophysics is used in hazard classification in areas that have been affected or may be affected by geohazards. So that's another discussion off on the side. And then we've also, over the last few years, been chairing a discussion around the establishment of a geophysical test site at the Vredefort impact site in South Africa. You can see at the top, I hope you can see it. I've got a little panel that's hiding my screen. There's a number of participants in this initiative, being a number of the airborne geophysical services providers, as well as software providers and academic institutions. So why Vredefort? The idea behind this was that geophysical test sites are quite sparsely distributed around the globe, and especially for airborne calibration facilities. There's one in Australia, there's a radiometric calibration facility in Namibia, and there's another one fledgling sort of very fleeting facility, I think, was established in Nigeria for some time. So we've brought a number of stakeholders to the table around this initiative. There is vast data opportunities that exist in this area. There's immense wealth of studies that have been conducted at various scales. There's continental scale studies that have been conducted through the likes of AfricaArray and the SAMTEX initiatives. There are various airborne data sets that are available at varying resolutions, from long wavelength gravity to a collection of more recently digitized ground gravity data. There's ultra high resolution MIDAS data that's available. There is Falcon gravity gradiometry data that has been acquired. And then the likes of Geotech and Spectrum have committed to providing more contemporary data sets using the Spectrum airborne EM system and other airborne EM platforms like VTEM and ZTEM that you can see pictured there in the center. So there's a wealth of data and research opportunities that this presents, apart from the commercial opportunities for contractors to acquire data and calibrate their geophysical acquisition systems. So this could catalyze discussions around the value of geophysics. There's a much bigger discussion around how standards are established. We've recently had a number of conferences around standards, both geophysical and geological, and how that can be extended into the engineering and geohazard space. How we collaborate with the likes of the Council for Geoscience, and whether we can bring them on board as one of the hosts for the collaboration site, as this is part of the legislation that drives the establishment of the council. So setting standards with the council, I think, is a high priority for us. Sue presented earlier on the RCDP projects that are in the region. We should be having discussions around Department of Science and Technology and the establishment of special economic zones. It is the flavor not just of the day, but of the past few years. And if we do want to see the geophysical industry locally grow and flourish, we need to put stakes in the ground and stop companies closing up shop in South Africa and Southern Africa, and rather incentivize their establishment and resourcing out of the region. And last but not least, involving the academic institutions, the universities. There's a range of other opportunities that present themselves for both research and further discussions with all sorts of entities. There's a lot of geophysical development that's been done in Southern Africa. And what we would like to see is that SAGA becomes and sustains discussions with the various stakeholders and entities, being industrial, academic, government, through various funding sources, and continued development of geophysical systems and the graduation of the next generation of geoscientists out of our universities and into industry in our region. Thank you.
Thank you for that great talk, Reese. I'll ask anyone who has questions in the auditorium to just notify me. Otherwise, there are some in the chat here. First of all, Ray asks if it is possible to download any of the talks from the ICEG event in October.
We are just finalizing the registration completion for that event between SAGA and the SEG, who hosted the event. In terms of downloading the talks, that was part of the individual registration. So that was available for 1 month post the event. The abstracts will be circulated to the delegates.
Okay, and then we have another question here from Sianda. Why is geophysics not transformed, and what is the role of Saga in this front?
Thank you, Sianda. I don't know if I'm 100% sure about what you mean by transformed. You're welcome to unmute and have a discussion around that.
I'm more than happy. Can you hear me?
Yes.
Yeah, no. For example, you have a lot of white owned companies that are not owned by majority Black African people. That's number one. Number two, my observation is that, for your information, I also sit in the board of Council for Geoscience and in the technical committee. So I would actually see some of the procurement that we've experienced. There's no Black company that conducts the airborne or no Black company that conducts the seismic or whatever the method. So what is the participation of Black African people? In this case, their majority are actually in the class of geophysics. It seems like our white counterparts, they actually get employed straight away, and then our Black counterparts, they end up in banking.
So our stance, and I put this on, let me just scroll to that slide. So Saga provides a forum, a platform for discussion. It's not biased in any particular way. And we want to provide a forum where discussions like this can be had to afford equal opportunity engagement. We realize there's quite a diversity of stakeholders in the industry. I don't think we support the how do I phrase this carefully? We're not looking to force representation of any demographic into the industry. What we're looking to do is support equal opportunity for any demographic that wishes to participate in discussions around geophysics. Sue, you've got a question or a statement.
Sorry, I've got two things on here.
Sue, stop multitasking.
Let me turn one off. Hang on.
Maybe Musa can help with the echo multiple removal. Sianda, maybe you can contribute to the discussion in terms of how other entities are, or what discussions had in other forums.
Is that better?
Loud and clear.
Yeah, I just wanted to say thank you, Sianda, for bringing that up, and perhaps suggest that there needs to be some input from people like Sianda who are experiencing this and have contact with people of what Saga could actually do, because it is no good us trying to figure it out without any input. And I think, you know, we are trying this internship program at WITS. It's kind of fledgling and just getting going, but other suggestions would be more than welcome. And so please feel free to comment some more, Sianda, and help us with some suggestions or get involved more.
Okay, thanks for that, Sue and Sianda. We can maybe have a discussion in the chat. And yeah, future discussions on this topic would be good in a safe environment. It's now time for the lunch break. So thank you for that, Reese, for the great talk and the overview. Ray makes a good comment that if he is right in saying that Saga was founded in 1975, then it's time for a 50th anniversary celebration.
Yeah, I've just looked into the history of of Saga, and I guess I wrote that chapter, And I see they convened their first meeting in 1975, but they sort of were formally constituted in 1977. It's a little bit vague, but anyway, I just wouldn't want us to miss an opportunity for a party. So perhaps.
Okay, thanks everyone. We'll break for lunch and then return here at 2 o'clock. Thanks all.
Thank you.
Hi, Sianda.
Yes, so hi, how are you?
Sorry, I've got my iPad and my laptop on because one's working better than the other. No, I just wanted to say it's a really important point, and we, you bring up, and we have talked about it on the committee a bit, and I've tried to bring in the ideas of equity and such, but we really do need involvement and suggestions, and I mean, Saga can't employ hundreds of people. But even helping to identify people who are or underemployed and start building up a database and figuring out how we can upskill people is really important. So, any suggestions along those lines or anything you can think of would be more than welcome.
Look,
Sue and Sue, can I just interrupt? Do you know your conversation is public? That's
Yep.
if you know.
Yep.
Yeah, good.
No,
Carry on.
I think it should be, and I think anyone who's still here instead of running to lunch should join in. It's
Sure.
I think I have it.
Okay.
Look, so
But yes, thanks for the warning.
It's important to know, and of course, I have plenty of ideas, and we cannot, in a country that has a majority African people, still remain with a field that actually is anti-transformation. And of course, in my view, it is Saga's problem, or everyone's problem, that we transform and we move the country forward. So I agree with you. Perhaps my input as well as to how we can assist in shaping and transforming the industry so that it's more representative. It's something that I'm willing to take. We'll discuss, so I have your contact, we'll talk, because there's no use in developing African geophysicists to end up in banks all the time.
Well, if it brings the money to the science, Sianda, that's an important thing.
No, but our white counterparts remain and they become geophysicists. We didn't study banking, so we could have made a conscious decision to do a commerce, but the conditions force us into other fields because there is no space. So how do we make?
And I mean, you make an important point, Sianda. When you say something like "there's no space," is that, is it lack of access to equipment? Well, that's something we're trying to address with the intern program by making, figuring out how to make the WITS equipment available. Is it lack of access to finance, or what are the barriers that people are facing? There are a number of Black geophysics companies that are operating, outside of any recognition of Saga. I get people contacting me about them quite frequently, but a lot of them are run by people from out, non-South Africans. So what is it that Zimbabweans and Botswanas are operating companies here in South Africa that South Africans aren't able to? What are the barriers? And I think we need to look at that and maybe have some sessions on how to start a company, how to, when I taught recently the MSc by coursework, two of the South Africans were very interested in setting up with some of the cheaper equipment or less expensive equipment from Geotron. and getting started. So, you know, there's plenty of ideas out there, but I think we don't know what the barriers are, and I don't even think we know how to access people who aren't employed.
Yeah. Sianda, I think there's a sparsity of collaboration, interdisciplinarity, that is happening between geophysics and who our end clients should be. We need to make our conversations more relevant, as opposed to, or more applied at least.
I'm not sure what you mean by
end clients. Sorry, Sue?
I don't know what you mean by that, Reese.
So we, and you mentioned it now, is that there's a number of companies that are providing what should be considered geophysical services. Some of those are black, some of those are white. Personally, I don't differentiate between the two. And they are not part of the collective discussion. They're not part of the Geophysical Association. They are just commercial entities, and they're going about their business, running businesses.
Oh, but there's a lot of companies out there that are not part of Saga. I mean, that's another issue we have, is that we have a very poor database of what's going on in the country.
You know, to stimulate industry, we need to be engaging our population, and the contribution that our educational system has on disenfranchising the average person in this country cannot be underestimated. We have an exceptionally poor ability to graduate learners out of school with any level of academic ability to put them in good stead to enter tertiary education in the first place. And unless that's addressed, it makes our job very difficult. So I think a lot of the bias that we're seeing stems from early education. That being said, where Saga can take over is in connecting various stakeholders in the industry, across the industry. And I've had discussions with you, Sianda, and a number of other people about the establishment of incubation hubs, where entities can be started, where individuals can acquire the necessary skills to enter industry and contribute and develop the critical mass that's required to continue with a viable business and not go to banking.
Yeah,
I don't know if Sianda's still there.
No, I agree with you. I think we are getting somewhere. That's why it's important to have these conversations. And I'm liking the idea where we can incubate, and of course, in our several interactions with the established guys, if they can work with the smaller guys, and so I like that idea. And I think maybe we should have some gathering, and then we reduce these things in
Just a very, very simple question is, who's aware that today, tomorrow, and Friday is the Science Forum South Africa?
I don't know, for example.
And next year, December, the World Science Forum is going to be hosted in Cape Town.
Well, I don't know. You see, that's a problem.
I mean, this is a phenomenal opportunity. The Science Forum South Africa is free to attend. It was free to attend in person. It's now free to attend online. You know, these are opportunities to collaborate with stakeholders in science from not just South Africa, from everywhere in the world. And we're not even taking the opportunity to do it locally in South Africa when something like the Science Forum South Africa is being hosted by the Department of Science and Technology. If we're not even aware of it, we're definitely not part of the discussion. And we're not going to divert and allocate resources where we would like to see them diverted and allocated. But it's not incumbent upon the volunteers in the executive committee of the Geophysical Association to have all the discussions themselves. We need the critical mass of the membership, and not just the membership, the entire industry, around a table with all the stakeholders. Or just one stakeholder at a time. It's how you eat an elephant.
Sianda, have you got some specific ideas about how to formulate some of the opportunities?
The way I was thinking of it is actually to go back and check and perhaps do some study. We can work with status at graduates produced by geoscience. It's specifically in this case, maybe might be geophysics, and look where they are. Because you'll find then a lot of them are displaced, at least the ones that I interact with, they've moved on. And then you look at what path can we create and security of jobs can we create for them. I'll make an example. When you are a mining engineer, it's by law that a mine must have a mining engineer. In South Africa, you have a persisting problems of fall of grounds and seismicity, but you have no law that compels a mine to have a seismologist. And what ends up happening, you get outsourced at IMS, and IMS tells you that, hey, they don't deal with only South Africa, they deal with Australia and Canada, and therefore there's no responsibility for them to transfer. So in my view, first, make it legal for mines to have a seismologist when they have a seismology problem and the fall of ground problem. That's number one. So you provide a security of jobs for seismologists that are studying at VETS. They have a clear path that they follow. Secondly, we must provide a very clear path, even in exploration, where we say that a graduate of seismology or a graduate of a reflection seismic or of geophysics in general has this clear path like CAs. You go in the first year, this is the training standardized, this is what you need to know. Second year, you can write an exam or board exam, or there's some what you call ratings to assess whether these skills have been achieved. And then this second year, you are now a professional geophysics, and then you are actually enabled to conduct work on your own. Because so even though you have these people who are doing all these random things on the side, they are not principal scientists, and therefore their work is not that of value. They do it, and then someone else signs, and then that's why you end up having no control and extremely poor level of geophysical reports that seem like they were written by a grade 2. I always tell you stories. I meet some random people who don't know geophysics. They are carrying GPRs, and those people also deal with the credibility of geophysics as a profession, and that's why a streamlining and a very clear standard must be set, because it won't assist. I mean, I met people at mining in there, but they don't want to see or hear anything about geophysics, because some bogus people come and claim all sorts of things.
That gets
those are very good points.
SACNASP registration, and Reese, I can't remember. We're still kind of in a ambiguous area there as far as geophysics goes, isn't it?
Correct. So, Sianda, you touched on a very good point, and that's the point of competency and being certified competent. Currently, the convention in South Africa is through SACNASP for geological sciences. Geophysics does not stand alone on its own 2 feet. And the process, I think, is quite vague. And I think that's as a result of SACNASP's process. If you look at other professional bodies around the world, there is a more rigorous competency assessment that's completed. In South Africa through SACNASP, it's essentially by consensus of your peers. So one would be recommended by one's peers to be competent. There's a few minimum criteria that apply, but yeah, that's where it's at the moment. In terms of making mining engineers mandatory, I think it's a complex topic. In certain disciplines, there are mandatory requirements for individuals But I think the global discussion is swinging towards the requirement for standards and standards of work, not necessarily mandating that it needs to be done by a mining engineer. It's a little ambiguous because one would have to determine that the standard was kept, and that's generally done by having a competent person sign off on the work that was done. But it is something that was discussed quite extensively at the ICEG conference, what was it, 2 months ago now, around standards and the incorporation of standards on geophysical surveying and the data products, specifically in the engineering space, so civil engineering space. But in my personal opinion, I think there is a sparsity of standards, but it requires us as a discipline, as a collection of experts in geophysics, to stand together and to talk with our clients so that they can understand that standards can be established. I think we're at the stage now where we're consciously incompetent, in the sense that we know standards could be established, but no one's doing anything about it.
What do people who are you're communicating with, Sianda, what are they saying would be, what are the top 3 things that would be most helpful?
Look, I think people go into geophysics simply because they come to VET and someone talks about this nice field and then they join, they get excited. But firstly, for me, the security of jobs. Number 2, it's some form of clear path that one needs to follow. And then, of course, that clear path, perhaps that's where you derive equal opportunities, because race assumes that equal opportunity are there. But if they are not streamlined in a manner that everyone gets that equal opportunity, and not through some coffee or prize somewhere where others do not get access to those prizes, then equal opportunities are not there in reality. So for me, how do we streamline these opportunities to be accessible to everyone who is in this field? It could be some generalized internship or program, or it could be these incubations that perhaps Rhys is talking about for those who want to explore the entrepreneurship routes. But for now, it is not clear to me where a geophysics student in South Africa works. It's just not clear.
So would having a series of talks about from different geophysicists in different industries, would that sort of thing be helpful to have those recorded and online?
Yes, but opportunities then must be streamlined and made available. It could be that we use also the same platforms to advertise opportunities and to encourage people to apply. And if there is some cultural gap or some gap that exists, and then maybe a SAGA tries and workshop that gap so that it can be closed. If there is some cultural gaps, there are some things that maybe some students are not aware of or don't know, and that's why maybe they don't get the jobs.
Yeah, I think Women in Mining has done a very good job on that. They've done a lot of work on transformation and seem to be quite successful.
Is there anyone here from not South Africa? Maybe if you are, you can contribute to how these challenges are being addressed outside of our borders. Sianda, I must contradict you there. I don't assume that opportunities are equal. I think equal opportunity is something that we strive for. So we understand our resources are finite and limited, and we're trying to place resources where they will make the most difference in order to provide more equality of opportunity. SAGA has, on numerous occasions across the last couple of decades, I imagine, sponsored individuals to go and study. That doesn't necessarily help you when you graduate, though. I know when I graduated, the path for geophysicists out of university was quite clear. You went to one of the mining houses. And they put you on what was called a GIT program, a geologist in training. And you would spend a year moving across various diagonals within the business, understanding how the different parts of the business operate. And that's something that we don't have anymore. Most of the majors stopped those programs in the mid-2000s. It is something that's been spoken about quite extensively, as I said, with these incubation hub ideas or with the Mandela mining precinct. I know the last few times I've been to the mining precinct that's established and supported by the CSIR, it's derelict. There's no one there. There's an association or two represented, but where are the entrepreneurs in the geoscience space? Where are the entrepreneurs in the mining space? They're certainly not present at the mining precinct. So how do we incentivize opportunities like that? Do we need additional tax breaks, like forming a special economic zone around the mining precinct? I don't think that exists just yet. But it takes the stakeholders, the people that are interested in it, to have the conversations with the powers that be to establish things like this. And it takes time, it takes effort.
Sanda, I'm thinking about your three comments there, and I think there's something that can be done fairly quickly that might, at least help clarify some things. You make the point about job security, and of course we know in the geoscience industry there's nothing too secure. But what if we were to put like a series of employers and kind of with a not too strict ranking, but something like the council, the average time that people spend employed by the council is 20 years, whereas the average time people spend employed by a junior company is 2 years. If we put something like that up in terms of, or put a document together or a video or something like that, do you think that would be helpful? And also for the other things you said, like the clear path. I mean, in general now, a master's internationally and even locally is becoming the minimum, partly because all these programs that Reese mentioned have stopped. That they kind of took the place of masters, or masters took the place of them. So I'm just, I like the things you've pointed out here, these kind of three tangible objects that we can address right away and actually put something up and try to clarify how people go about, really getting a job. Because most of us have been out of it for so long, we don't even know what the issues are.
Thanks. So what is actually interesting is that there seems to be some effort from Council for Geoscience. They are trying to now conduct some integrated mapping using high resolution methods.
Oh, they're got huge funding. Yeah, absolutely.
So part of what also I've been raising on that side of the world is them having some ESD. Not every procurement opportunity must be a large seismic survey. So how do we then break these things down and incorporate the incubation that Reese is talking about? Because we then begin to start a triangle where you have universities on board, where some opportunities they can use this equipment to lend to students or to these qualified or people who are being incubated to conduct these surveys. And then because you do need this principal thing from SACNESP, then someone must mentor and someone must be willing to say, go do the work, I will do the quality control and I will sign on your behalf, so that we can also deal with the issues of standards. Because transformation must not mean that some poor standards. how do we, in fact, maintain or actually rise the standard while we effect a transformation? And then on the other side of council, where they have these programs that are geotechnical mapping, then they avail those opportunities, but they know that you have some, we are working with some credible company, there is some credible institutions also like VETS that are backing those. So we create this triangle. And I'm more than happy to have all these stakeholders in one room, and we discuss a blueprint on how we actually firstly deal with the issues of standards and competency, security of jobs, and the transformation.
No, I like that. That's really good. And it's a question of what tangible things can we do to really put some stuff out there. And I think one of the things we at the university, I mean, a lot of it just takes money and opportunity, but certainly one of the things we can do that I think perhaps we haven't been very clear about is what does job security mean in the geosciences, and what different what different career paths have different security, and what is the path to get a job. It's been interesting to me to watch. I always talk about networking, and I give a whole lecture over to career development, and it's interesting to me to watch who embraces that and who doesn't, and how people embrace it differently, and how quickly people get jobs sometimes when you wouldn't expect them to, when they do start networking, and how can we facilitate networking, even that simple. So it's I'll think about that, and maybe we can chat about some just specific small things that we can get started with right away, while we think about a bigger picture. I've got to run get some lunch.
Okay. No, maybe just one comment. We can actually look at SICA. I don't know if you know SICA, which deals with the accounting and the CA.
No, I have no.
Yeah, maybe we can visit SICA. They have a very quite rigorous process. But of course, what they also do is to do these board exams, and they do these assessments. They place these graduates into these big accounting firms and all of those things.
Yeah.
Now, when I say security, you see risk. One, you need some form of legislation, because also these King 4s and some PFMA, they require some auditing. So they don't exist for the sake of existing or innovative. No, it's law. They must do it. So I won't go in a field where I must go in the back. No, government must legalize, and then we go do the work. If you think you are going to just do things, it's not going to happen.
Yeah, I'm not what you mean, but yeah. And
I agree, Siando.
It's hard with the standards are very different internationally, country to country, and a lot of it has to do with, it's a big difference between accounting, where you can be correct to the absolute penny, and geophysics, where we might drill a 2-kilometer borehole and there's no target down there. So it's very different types of scenarios.
But as we speak, it's law that gravity must be conducted in places where there is a dolomite. But we have not taken some time to upgrade that. Gravity is not the only geophysics method that is applicable in those regions. So I'm giving you an example where geophysics is legislated. I'm saying that you can legislate it throughout when it comes to infrastructure development, when it comes to exploration, when it comes to anything. Because a competence person's reports needs some a geologist to sign it off. So, but I'm just saying that there are clever ways into legislating our own skills, and that provides a security of jobs for me. Thanks.
And I think you mentioned also the use of GPR, and that was another one that was legislated, because 10 years ago you didn't have to do a survey before you dug up the street, and now you do, and that survey is usually a GPR survey. So it's interesting how that has changed too.
Yes, and then there we need to add geophysics must do, so that we can do the competence and the standards.
Yeah, yeah. But again, I don't think that's, you know, that's, the question is whose role is that and how does that get done? And it's certainly not something I would.
We can actually table a paper to the relevant government authority, or a presentation. We go to parliament, we lobby. That's for me, I'm willing to do, because that's where science falls short, is that they don't actually push as much as engineers. Engineers are very good at legalizing everything they do, and accountants.
Yeah, no, and you know, honestly, I wouldn't know how and I wouldn't know where to start, but I'd be happy to support your initiative there. I certainly think anything listed on the stock exchange should have some geophysics backing it up too.
You see, that's where you make money. You tell them that, hey, this thing of data is bogus if you don't have a geophysicist signing on it.
There you go. But and SAGO is probably more appropriate to get involved with that than, say, the university, because it falls far from our core business.
Yes, SAGA is the right platform, but also I think Rhys is making a very good point that even at SAGA, they are not well organized in terms of the broader industry view, and you probably need some little bit of roadshow, engaging people and making sure that they buy into the idea, so that when we go and approach politicians will only listen to you if you are organized.
Yeah, yeah. Go for it.
Yeah, I'm happy. I will do it. If you will prepare something and then look at where we can actually start, and then we.
I think Sianda's just volunteered to be the lead of our lobbying subcommittee.
I think so.
Aye, Chief, that I'm open. That's what I do best, anyways.
That's where your skills are. That's wonderful.
Not science.
Sianda's specifically on the incubation topic. You mentioned, you know, equipment availability and the availability of people and time resources. It's something I've had a discussion with a number of individuals on this call about, and I see there's a clear niche here, and that's not to directly compete head to head with commercial services providers, because there are service providers providing a range of geophysical services, and that's commercial, it's their business. But there's certain scales of operations that are not economic. It's not viable. And generally those are around proof of concept studies.
Yeah.
So will a particular geophysical method be value adding in a particular geological or geotechnical or engineering scenario? And I think there's a massive space there to grow the exposure of geophysical methods and to increase the number of jobs required in the geophysical industry, because there's more uptake of the methods. And it's that proof of concept. It's going out and solving existing problems that are not currently being addressed with any other methods, or where geophysics can do it cheaper or faster.
And there is research money, you know, available for that. It's been difficult to access because most of the small contractors are too small to really take on research responsibilities. So it's a catch-22.
So another entity that's also on as part of this discussion.
I'm going to pull out now because I've got some things going on here at the house with electricity, but really great.
I also need to eat.
Yeah, thank you very much, Sianda, for bringing that up, and thank you, Rhys, for great input.
So here's a parting thought. Have a look at the entity called ProSet, which is a collection of professional bodies coordinated by the NSTF.
Yeah,
and they have various funding opportunities as well, for which we've applied.
It's called ProSet, eh?
Correct.
Okay, no, thank you. I'll look.
Okay. Cheers.
Hi, Sarah. Hi, Sarah, are you there?
I'm here. Hi.
Hi. Hi. How are you doing?
Good. How are you?
No, I'm pretty well. Just
Well.
got a bit of a croaky throat and things like that. While Margie's just taken herself off to bed, so she's feeling a bit feverish. But we good. Yeah, no, and the morning's gone well so fast. As you're looking for everybody, we on a lunch break, and so for another 15 minutes is when we're due to start again.
Okay. So did the
Right.
schedule change?
Well, I'm not. I guess it probably did.
Okay.
Because the latest version that I've got here, and I suppose if you go to, I think I can't remember what I forwarded to you, but in the latest version, you're down for a talk at 16:15. This.
Oh. Yeah,
Okay.
the one I have, it is at 1400.
Okay.
Okay. 16.
So I'm sorry if you've got up. Yeah, no, this has all been very, that this latest version. And I suppose if you go to, let's see, what did I send you? Let me just, and if you click on that link, and it will take you to a website that's been created. And
Okay. Okay.
I think I sent something to you at,
You did.
oh gosh. Okay, let's just see. What did I do? I forwarded something to you at 9:46 my time today, and the meeting started at 9 a.m. today and is going well. Okay, and if you can you find that? I sent it to you and Andy.
Yes, I found it.
And if you scroll down there, you'll see the program
Got
and
it.
the link. And if you click on somewhere down there, there's a AfricaArray website. Now we've built a website while we were there for this meeting. If you click on there, you should be able to source the program.
I do have it now. Let me see if, gosh, I hope I can make this time. Let me check.
But let me say it's going very well. I mean, there's some things that were a little bit last minute and a few little hiccups with all the links and attaching together. But in fact, the whole technology's been working surprisingly well. I think if you click on events, I think is where you're going to do events, and then you'll find yourself program somewhere there.
I'm just trying to figure out the time. Let's see.
Yes, and then then you go down to events, and then you go down there. It comes to download program somewhere there.
Yes, I do have it. Let's see.
So yeah, okay, and that's the one that we are. Well, when I say we run into, of course, there've been one or two minor modifications since then, but it's yeah.
Okay, so 16, 15. Africa time. Oh, so that's 9:15 for me.
Okay, so the time right now here is 13:47 for me. What's it for you?
It's 6:48 for me.
Okay, 6:48. Yeah, so there's a 7-hour time gap there. Yeah.
Well, I will come back on then at about 1600.
Okay.
Okay.
Great.
So that'll be right after y'all's tea break.
Yeah.
Yeah. Okay.
Good. No, well, that'll be great. Okay. Now, and if anybody asks, I can say we spoke. So yeah, we're on track.
Perfect.
There.
Yeah. All right. Thank you so
No,
much.
thank you, and enjoy your.
Right,
Have a good breakfast. Have you had your first coffee yet?
Thank you. All right. Bye.
Bye, Sarah.
Welcome back, everyone, to our next session. So I'm the new chair for this session. My name is Sally Zwaplaki, and I'm an MSc student here at Wits University. So on to our next theme, which is earthquakes and mining seismology, as well as ICDP projects. So we're going to be preparing for our first speaker. Just going to give him some time to prepare. Who is Thulani Maupa from the Council for Geoscience in South Africa. And his talk is titled, Geological Investigation of the Possible Source and Quantity of Coal Bed Methane in the Highveld Coal Fields. So if Thulani could please indicate that he's around, we'll start whenever you're ready, sir.
I'm here, Mhlegas. Good afternoon.
Afternoon, Mhlegas.
Oh, great. I was almost thinking kidnapped at Westgate then for some reason. All right. And share my screen. It's sharing now. It should be visible. You can give me an indication.
We can see it.
Yes, it is visible.
Thank you. On my watch, it says 13:59. You said you were giving me time to prepare. I'm in your hands.
You may start.
Thank you. Afternoon, everyone. The name is Thulani Maupa. I'm also an MSc student at Wits University, and I think I should put a disclaimer here, having followed through the discussions over lunch. It was quite interesting. So I'm not a geophysicist, but a geologist attempting to do geophysics. And also, maybe just to mention that the views expressed here won't necessarily represent those of the council, but will be my own. Sorry about that. Some people have perfect timing to start calling when you are engaged in a presentation. Okay, this study is a geological investigation of the possible sources and quantity of coal bed methane in the Highveld. The idea was to focus in the area around Bethal, where we've got some legacy seismic data that we were going to look at. Just struggling to get my screen to move here. Sorry about that, I'm just frozen. I can't move between my slides. And everything was working perfectly now over lunch. Even presentation mode again. Let me try and go back and see if it will work this time. Yes, it seems like it will work.
I think it's cool. Fired power.
Sorry? Okay, here's the structure of my presentation. I'll talk about the problem or problems, the aim of my studies, the data processing, and the way forward. Here's one of the problems that we've identified. One will start wondering, because in my topic, I'm talking about coal bed methane. Where does CO2 come in this whole picture? It's one of the challenges was, for those who've been aware, we've been trying to pilot the CO2 storage potential in a number of basins, with the Zululand Basin in northern KZN being one of the focus areas. But with the challenges that we've been facing there, I think what part of the suggestion from the Minister Gwede Mantashe, was that why not look at operations closer to emissions, which makes sense because otherwise we would still have had to transport CO2 over 600 kilometers to the injection site. Again, there's also the Paris Agreement 2016, wherein the minister has been now vocal about talking about just transition, which means that much as we're saying, yes, there's a problem with global emissions. South Africa cannot afford at this stage to let go of its coal power stations. And obviously, most of you would be aware of the recent announcements that were made on our behalf following the COP26 in Glasgow. I wouldn't want to say much about that. I'll just leave it at that. Now, coming back to another real problem that we are facing. These are statistics between 1982 and 1993 of explosions in underground mines in South Africa, not necessarily coal. What I want us to focus on here, let me get my pointer. If we look at this graphs here, the second one, it shows you the explosions that have occurred in underground coal mines, with the others being ignitions, whether it's ignited or not. Now you'll notice that between 1991 and 1993, there was only one incident of ignition that occurred in underground mines in South Africa. But unfortunately, the one incident in 1993 from just one explosion resulted in a death of 53 people in the underground coal mine at Sasol's Middelbelt Colliery in Secunda. This obviously is a stat from 1993. Unfortunately, 2 or 3 days ago, we saw again another occurrence where we still have miners dying underground. Whether it's mud rush or roof falls or it's coal dust explosion or whatever the case may be. We've always said that one life lost in mining operations is one life too many. And I think we were all listening to the Dean this morning when he was talking or challenging us as scientists to say we need to start finding solutions to these issues. And I think we are better positioned as Wits University, seeing that close to being 100 years next year. I mean, we started as a school of mines. And I should say it is not acceptable that we're still getting incidences where people still die underground. Yes, they may have tried to engineer it out in the coal mines by applying stone dust so that we don't have methane ignitions resulting in coal dust explosions. We try and engineer everything that we can think of. One can think of the Mary Spruit disaster, where a failure in a mine dump again resulted in the flooding of a whole town with people dying. Did we really not know about the rain that we are going to have over the past weekend so that we can prevent this mud rush going into the mines in the platinum belt? So these are challenges that are facing us as engineers to say, what solutions are we coming up in this age of IR to make sure that we avert everything possible to make sure we save the lives of people? Now, coming back to my issue about methane, again, this is something recent. We would have seen this article. It came out on the 16th of June, where it's talking about a large methane leak detected over South African coal mining operation. And from the reports there, they indicate that there was a cloud which was spotted 125 kilometers east of Johannesburg. That area we know is now Secunda. Unfortunately, both operators in the area deny any knowledge. That is being Anglo Isibonelo Colliery, which is an open cast mine, and we had Sasol that has operated in the area for over decades. This, for instance, is the underground operations of Sasol Colliery. Now, from what we know, about 55% of coal is extracted from underground. You can try and increase the percentage a bit by doing total extraction, but then that results in golfing and fall of grounds and then so forth and so forth. So the coal that remains behind, is it still sufficient enough to hold methane that can result in what has recently been picked up? I think the report there was talking about 60 tons per hour of methane that was released over a period. In fact, they picked up 2 incidences. The first one was on the 10th of May, and another one on the 17th of May, where there's these methane emissions that are picked up from from satellites, but none of the sensors and everyone on the ground can actually account and say, yes, we do know about this. So it does remain a problem. Ultimately, it's going to end up being a problem for government, like we've had with all the gold mine dams in Johannesburg and every other problem, acid mine drainage in the collieries in Mpumalanga and so forth. So these are challenges that challenges us as young scientists to say, what are we doing about it to make sure that we mitigate against this? Because again, the issue of saying we need to preserve what we have. I think Prof. Jill also touched on this to say, let's try and preserve everything that we have, not only for ourselves, but for future generations. Now, coming back to my study, the aim is to understand and interpret the legacy 2D seismic data in order to identify geological structure that could possibly act as migration pathways for coal bed methane. Now, here's a map of the area, trying to zoom into the area that I'm looking at. So you can see there's Secunda there with all its coal mining and the petrochemical operations. And there's an area in Bethal. And these are the seismic lines, the legacy data that I'm looking at for my study. Now, prior to this, when I started this exercise, I actually realized that we're in a unique area which exists. You've got the extension of the Wits Basin in the Evander goldfields, just to the west of the area here. And to the north or northeast, we have the Bethal lobe of the Bushveld complex that cuts across this area. Unfortunately, there's not much drilling happened because most of the drilling, you can see that it was mainly focused on the gold exploration and the related operations in the area. But again, there's a whole lot of other data that exist, much as we might not have access to it, for all the coal exploration that happened in the area. Now, this is one of the boreholes that I picked up, just a random borehole. This was drilled by Genco in 1989. And you can see even from the core logging that the main focus was just to target the gold. Nothing else, nothing much on the geology that lies above. Now, from what we have done so far, we've now managed to take this data, try and locate some of the boreholes, which I was fortunate to locate one of these boreholes at the National Core Library of the Council for Geoscience in Donkerhoek in Pretoria. So this is part of the work that we have been doing. So you can see that from this, we managed to take what was just logged as one dolomite unit to try and now find where we identify these shale bands that occur within the dolomitic units of the Transvaal. Even better so, because for the project that I'm currently involved with, we are looking now at the lower Ventersdorp lavas for possible CO2 storage in the basaltic formations of the Ventersdorp. Again, you can see that the target for them was mainly the gold in the Wits Basin. So you can see with the Wits Basin, you get your clean quartzites and you still get those shales that have been metamorphosed. We've seen in the gold mines where these shales are actually the source for the methane that migrates to cause methane explosions in the gold mines. Now we've looked back at the data, and this again is information that is very helpful because with the underground mining at Evander goldfields, they've now mapped the structure. We can actually now access the faulting and the structure so that it can assist us to identify the faults. From the data that we have, which is now, I'm talking about the legacy data, most of it, there's no wireline logging. So we had to take, basically, or we practically have to take some samples so that we can try and do some rock physical properties by doing density measurements, measuring the S&P waves, so that ultimately we can produce the synthetic seismograms. That information hopefully will be able to help us to interpret some of these legacy seismic, 2D seismic that we have. I've just picked up one of the 5 as an example, where you can see clearly the way the Karoo is actually clearly delineated on top. And then on this specific one, I spoke about the pedal lobe of the bushveld complex to the east. So we can see there's the Transvaal there. And, oh, sorry, that would be the bushveld, which is the contact between the bushveld and what lies above. And then you also get clear reflections of some of the rocks, which we still need to identify. I think having looked at the data, it might be that we have the Black Reef continuous around this area, because it also has a very sharp and nice competency contrast between the surrounding rocks. So here's the challenge. We've now evolved through this data capturing, drilling of boreholes and all that. We are now at a stage where we need to now start applying this 4IR so that we can reprocess the available data, because it costs a lot of money to acquire this data. It's all available now at our disposal. We just need to make sure that we understand everything, or at least try and extract as much information as possible from what we can get from this data, so that when we start to develop projects or advise people who are developing projects, at least we are coming from a better footing in terms of science understanding. So the way forward, I would say, having looked at the data and having engaged with a number of people, is there a possibility that there can be an extension of the Wits Basin beyond the current limits of what we know within the Evander Basin of the Wits Basin? This is one question that will need science to try and find out. Again, I mentioned the issue of identifying storage potential for CO2 in the existing rocks within the basin. Yes, we know about storage within the sedimentary basins, but now there's also another opportunity of storage within the basaltic formations of a Ventersdorp. Again, we can use the structural interpretation from the current study to see whether can we also predict to say that once we've injected now this CO2, will it now find the very same fractures and faults to escape? Because the idea is that when we store, we must store it permanently. This is for cleaning, for trying to clean the atmosphere. And lastly, I would like to thank my current employers, the Council of Geoscience, and also the Wits Seismic Research Center, which was labeled, I think, the Dry Lab earlier this morning, for access to the data and for helping fund these studies. Thank you.
Thank you, Mhlekazi. Are there any questions for uThulani? I don't see any online. From the floor, are there any questions for Thulani? Okay, Mhlekazi, I don't think there are any questions, so thank you very much. Now moving on.
Thank you very much.
To our next speaker. Sorry. Moving on to our next speaker, whose talk is going to be titled "The Statistical and Machine Learning Approach to Analyzing Faults and Dikes at South Deep Gold Mine." That would be none other than myself. So, can you guys see my screen? Yeah. Now you can see it.
We can't see it online.
Okay.
There we go.
Can you hear? Okay. Okay. My name is Sally Zoblaki, and today I'm going to be presenting my work, which, as I said, is titled "The Statistical and Machine Learning Approach to Analyzing Faults and Dikes at South Deep Gold Mine." My work is done under the supervision of Professor Musa Manzi and Professor Glenn Weiler. So this is the standard outline of my talk. So in 2003, Clove South Deep conducted a 3D survey, which was done by the French company CGG. This was to map the reflecting gold-bearing horizons, the VCR and the Black Reef. So interpretation by Manzi first in 2012 and then in 2020 and 2021 showed that the VCR is cross-cut and intruded by multiple dikes and fault systems. The mapping of dikes and faults at South Deep is important because the dikes complicate mining and may even be conduits of water. The faults displace the VCR and can cause seismicity. Also, due to the low seismic resolution and complexities of the structures of South Deep, further statistical analysis of the orientation and geometry of the major structures is therefore necessary, and is the majority of the content of this work that I did. So South Deep Gold Mine is located 45 kilometers southwest of Johannesburg in the town of Westenoria. They're currently mining the Upper Elsburg Reef, which is mapped by seismics using the overlaying high-velocity femtostop contact reef, since the Upper Elsburg Reef is seismically transparent. And this is basically the structure of the ore body at South Deep. So interpretation by Manzi, as seen in figure 3, showed various structures, but most notably was the range fault, which is a fault which divides a South Deep into 2 distinct blocks, south of range fault and north of range fault. Locally, this is how you'd be directed around the mine. And also, this was done to map major structures and small structures. Basically, major structures are structures which have a throw that is greater than 25 meters, and smaller structures are the opposite. And also to map a very prominent dike, which is the Gemsbokfontein dike, which trends north-south at South Deep. It's the topic of conversation at South Deep because it's home to quite a lot of incidents that happens at the mine and many other reasons. So these 2 structures, the range fault and the Gemsbok dike, were of particular focus in our study. And in figure 2, you can see the area of where the surveys were conducted, most notably the 2003 Clove South Deep 3D seismic survey, which basically mapped a bit of both mines. Now, the mapping of these structures by traditional seismic interpretation software shows less structural complexity and topographical variation of the 3D surfaces. The surfaces are also not mapped beyond the mapped, are also not continuous beyond the mapped region due to low seismic faults in these areas. And also the range fault surface is not well defined and it exhibits less structural complexity than expected, i.e. Gibson first interpreted the structures in 2006. And so the range fault from this was expected to be much more complex due to how it interacts with the ore body at South Deep. So the aims of our study was to reevaluate the local structural complexity surrounding the range fault and the Gemsbokfontein dike. And to do this, we had to represent the orientation of the major structures, which cross-cut the ore body, as well as describe the range fault's relationship with the VCR. Also improve the surface fitting methods for both the Gemsbokfontein dike as well as the VCR, and then improve the detection of small and large structures in the northeastern portion of the mine, which is South Deep's current area of interest, and also establish a machine learning model which describes the vertical displacement of the range fault at the VCR level. To do this, we use various tools. Most basic was the StereoNet diagrams, both 2-dimensional and 3-dimensional, as well as the rows diagrams, which are basically orientation histograms. This was done to illustrate the dip and the dip directions. To do the StereoNets, we use StereoNet 11, which is an open source free software. And we also use MATLAB. To do the surface fitting, we used MATLAB, specifically the thin plate splines, because unlike traditional interpolation method, the thin plate splines consider the elastic properties of the surface, such as the bending energy of the fault. So the whole concept of thin plate splines is based on the bending energy of which the surfaces that you're trying to fit obey. So which is very powerful if you think about it, because the stratigraphic layers such as VCR and so on, they follow these mechanics, the similar type of rock mechanics. And so these can be very powerful, but computationally, mathematically, they define points of minimal feasible and maximum feasible ranges, which you can then define a limit or as a breaking point. So they pretty much mimic layers of rock. And finally, the machine learning was done specifically, it was a regression problem to predict the throw along a fault. And this was done using the Gaussian process regression. There's a standard machine learning workflow, which is data collection, data pre-processing, model training, model evaluation, and finally improving the performance of the model overall after evaluation. And this is what our data looks like. I know it's not quite clear, but there was quite a lot of data having multiple features. Some of the data is missing. So basically, machine learning is going to illustrate the power of improving missing data points, sparse data points, and etc. So in total, there were 126 structures. And these, for each structure, there were the following features. So there were the X, Y coordinates. These count as 3 features, and they were in LO27 format. And then the dip angle, which was pre-processed to have minimum, maximum, and delta and mean features, as well as the dip direction angle, azimuth, and throw. So the prediction of reef along the VCR was done using Gaussian process regression. So currently from figure 10A, you can see how complex and non-linear the throw along the along the fault is of the VCR. So as you can see, this does not exhibit any straightforward relationship. So further investigation of this relationship is very necessary in order to predict the vertical displacement. And yeah, so the validation and model, it's just that I can't see the top of my slide. So K-fold cross validation was used to assess and improve the predictive performance of our GPR model. So this basically involves standard steps, such as the first fold is used as a validation set, and then GPR is applied to the remaining folds. And then the mean squared area is computed for the observations in the first fold, which is the holdout fold. And then we repeat this K times. So in our data set, we use 5, which was quite standard and worked quite well. So, and then ultimately we then compute the cross validation error, which is shown there. So basically, this is a nice illustration of how the whole cross-validation works throughout the data. And then ultimately, we had to tune the hyperparameter. So just a little summary on the GPR model. So GPR process, Gaussian process regression, is basically described by its mean and then also its covariance function, sometimes referred to as the kernel function. So the mean function is assumed to be 0 by normalization. And then the covariance of the kernel function, there's quite a variety to choose from. But for Gaussian models, there's usually ones that work very well. And the squared exponential function is one of them, which I chose to use. I did run several other ones, such as the quadratics, also the radial basis function, but they all are pretty much one family of functions. So, but in this particular example that I'm going to illustrate, I use squared exponential functions, which has this form. Now here, sigma squared and L are hyperparameters. Sigma is a hyperparameter which describes the covariance noise, which pretty much mathematically defines how much the function can vary vertically. And L defines how quickly the correlation between 2 points drops as the distance increases. So a fundamental concept of Gaussian process regression is the fact that it takes into account that points that are close together should have a similar output value. So that's the whole concept that it's built around. So I'll now illustrate how hyperparameter tuning of the model pretty much works. So what you're going to see on the right side is going to be how, on the left side, is going to be how the hyperparameters are varied. And then on the right side, it's going to show you how the model performs, the observed model compared to the estimated model. And then below, something should also, yeah, so pretty much, this is when I run the code that I wrote for tuning of the hyperparameters of the model. So as you can see, the iteration values, this is 30 iterations. I couldn't run this live because I didn't have a powerful enough device. But as you can see, the black points are the next points, the blue points are the points that it uses for the tuning of the model. And yeah, as you can see on the right-hand side, it pretty much smoothes out as you approach the final values. But it's, yeah, and then the model crashes. So that's a very important step of the whole process. And then finally, the model evaluation was based on the standard goodness of fit criterion, which includes R², which is also referred to as the coefficient of determination. Also R², the root mean squared, which is basically self-explanatory. So pretty much a model value that has an R² which is closer to 1 and an RMSE that is closer to 0 indicates a superior model performance. Finally, the model adequacy was examined using plots of residuals against predicted values. So with the basic stereo net interpretation, A is the area of interest, which had less structures pretty much, and they were much more localized. But what is good is that they exhibit a mean dip that we expected of around about 87. And then B is our regional area, which encompasses everything. So there we didn't expect much pattern to say, but in A, it's good that we see a southeast northwest trending structures, which is expected, which is also described by Manzi in 2020. Next up, when we look at the three-dimensional stereo nets, we can see that the dip angle of the structures in the area of interest is very vertical, which was also expected as described by Manzi and Gibson. So as you can see here, the good thing about the three-dimensional stereo nets is that they show you both the dip direction and the dip. If you have few enough structures, I know it becomes a hassle when there's a lot of structures. So when we look at the Gemsdijk, if you look at the Gemsdijk, previously there wasn't much structural variation or topographical variation along, but now as you can see, after applying the thin plate splines, it shows much more variation along the structure, which is very good, and also it performs quite well with not much computational intensiveness. So as you can see, the sum of squares error is 2.98 times 10 to the minus 4, which is pretty much 0. R² is very close to 1, it's pretty 0.995. So this is a very good result. Coming back to the range fault, as you can see, the range fault also exhibits much more structural complexity, which I was happy about. Also, it agreed with the gentle dip of around about 51 degrees towards the south of the mine, which was also quite good because not only does it agree with previous result, but also it adds more detail. So as you can see, I mean, you can compare from your eye the two structures of the range fault and the one predicted by the thin plate splines. And also it showed a strong output performance with the following goodness of fitness criterion, which was a sum of squares error 3.75 times 10 to the minus 9. That's pretty much 0. And then an R² of 1. So it performed quite well. And then finally, before I do the Gaussian process regression, I looked at some other predictive models such as decision trees. As you can see, they didn't do well. with an RMSE of 23 and an R squared is pretty much close to 0. But on the upside, it wasn't that computationally intensive, honestly. But also things that are wrong don't take much time. So when you use PCAs, which is principal components analysis, because I figured it works on the same principles as the GPR because they take points that are similar to each other. So it didn't improve much. It improved my RMSE by exactly 1. And R squared was 0.01, which pretty much still says the same thing, that predicting the throw of the range fault at the VCR level is not quite as straightforward as thought, needed a better model. And then finally, using the Gaussian process regression, as you can see, it did a wonderful fit. It predicted the throw over the structure. So it had the following output goodness of performance parameter. The R squared was 0.98 and the RMSE was 1.85 and the mean squared error is 3.42, which were very good outcomes. And also it was computationally efficient. It only took training time of 110 seconds, which is pretty much 2 minutes, with a predictive speed of 9,600 observations per second. So not only was it good, but also it took quite some good time. And as I said earlier, I did use 5-fold cross validations to avoid overfitting and improve the model overall. And so in conclusion and some future work, so as I said, in the area of interest, there's regular trends, which suggest that there's some underlying structural control. Also, the fact that the GPR models are promising to predict stochastic processes such as throw along with fault, and can be used to analyze other structures. And also we can do this by using multiple features, such as the ones I listed earlier, to predict more characteristics and maybe different variations of the GPR will yield some useful results. And then also the reappraisal of legacy data will also give a constrained structural analysis results of the range force relationship with the VCR by enhancing the detection of small structures. And also the thin plate splines may be improved by taking into account specific physical properties of the VCR, specifically the elastic properties of the thin plate splines. And I'd like to thank all the following for contributing to my work. And yeah, thank you. Are there any questions for our wonderful speaker? Let me go back to holy shit. Okay, it's taking a while to load the Zoom, but let me see in the chat. I don't see anything in the chat so far. Yeah. Yes, Prof.
Thanks, Elizabeth, for a good talk. Quick question. Can you use the same approach to predict the heave of the fault?
Yes, indeed, you can, because it's pretty much...
What will be your input parameters if you will have to do that?
I'd pretty much use the throw again, but then I'd actually need the actual value of the displacement, because pretty much it's a Pythagorean theorem. So if you have two sides, you can predict the third side. So, but as far as the physical relationship that goes between the heave and the displacement, I'm not aware of any methods that currently link the two relationships. But as a numerical problem, it is possible, because it's pretty much a Pythagorean thing. Okay. I think that's it. Okay. Now we move on to our next speaker. I just lost the... We move on to our next speaker, which is Emmanuel from University of the Witwatersrand. He's going to be giving us a quick talk. It's an in-person talk, so thanks, Emmanuel.
Good afternoon, colleagues. My name is Emmanuel Onyebueke. A postdoctoral research fellow at Seismic Research Center, School of Geosciences at VET. I will be presenting to you part of the project, which is we did at Maseve Mine. My colleagues have presented much part of this project, Kenneth Rapesa, and then quite a lot of corrections and comments was made, which is applicable to this result that I will be presenting to you. So I'll be presenting some section of the lines, which I did process myself. So quite the project is actually the same project. So I would like to thank CSR, Seismic Research Center, Mandela Mining Preset at VET, and AfricaArray for the opportunity given to us to always present and showcase our scientific evidence. So like my colleague have said, much of this project is to develop and acquire technologies and the technique that will be used to obtain information ahead of the mining phase, such as tunnel seismic prediction. So I won't really take much of your time in explaining what my colleagues have already presented. So we are trying to use a high resolution seismic method to obtain images ahead of the mining phase. And then secondly, how do we use this information to adopt in the mines for the safety of the mine workers? And then probably quite the same area that the project was done at Maseve Mining. And then this is the location. Actually, the project was designed in 3 sites at the Maseve Mine, which we have site 1, 2, and 3. Most of these are done at the surface. So we actually did the surface seismic and then again tunnel seismic. So much of our work presented here will be at the tunnel seismic, and then much work is still going on, and then much processing is still going on. Like Professor Musa has said, we're currently doing a lot of processing and then updating our models to return back. So quite is the same field. The data was conducted at Bushveld Complex. The diagram C there was the magnetic intensity map of the area, which also assisted us to image some structures that we could be interested in the site. We also did some field sampling of the rocks and then logged some boreholes there to obtain the information of the rocks so that we know actually the velocities and then the densities of the rock we are actually working with. Then the site 1 we deal with, the diagram here presented the field design, which we did on site 1. So we actually designed a kind of a 3D line, and then where we acquired both the active and passive seismic. We also did the same thing on site 2. So actually, these are the samples of pictures we did there. So this is actually the kind of forward modeling of trying to achieve what we get in the field. And then this is some kind of field pictures. And then in general, we use a remote acquisition unit, which is 394. Total recording time of 4 to 7 days, active and passive. We also use a land streamer, some brown band sensor, which kind of a real-time information of what is happening, because so this is actually the table of all the seismic line we obtain in the area, which my colleagues have processed some of the lines, and then I will be much interested in processing the line 1 and 3. This is some of the underlying on tunnel pictures, and then this is the where the lines were conducted inside the tunnel. This is the result, the data analysis, which I try to identify some of the noise, like at the field, the data you acquire in the field is actually determining the result, and then the final information that you will get. So quite like our supervisor has said, we don't have a lot of prior information, but we are going back to acquire more data, and then but the result and then the data we acquire, we won't say is top notch, and then we won't say is quite a bad data, but we work with it, and then we kind of extract as much as information we could in order to help us for our next project, which will be able to tell us more about the site. So this is probably the initial processing that went on the data, which is the linear move out, and then velocity frequency analysis. And then this diagram here shows much of the travel time plot in order to determine the velocity of the near surface, which will help us to kind of know the approximate velocity of the top fractured bedrock, or probably what will be the velocity of the direct wave, which could be as a result of the tunnel walls and then the fresh bedrock surrounding the lines. So this is the tomography of the line 1 and then the line 3. So quite the same velocity that my colleagues acquire is approximately the same velocity, and then which is like the top near surface at 0 to 5 meters, we have quite approximately 4,000 meters per second velocity. And then at the bedrock, we have approximately the velocity of the norite, which is about 6,500 meters per second. So we also did the reflection. So the reflection I did on line 1 and then line 3. This is the table that shows the processing step, which involved the normal conventional reflection seismic processing. And then without taking much of the time, this processing involved the geometry setup, trace editing, trace normalization, NGC, first break picking, which is resulted the tomography, Bruce stack, muting. And then at the final stage, we do the migration and then the time depth conversion. So the result, what we try to achieve is to have a stack result, which is the zero offset stack section of the result. So this is the preliminary result. I have along line 1 and 3, and then I could be able to identify the 4 reflections, but kindly working with the data we have, we are assuming that some of the reflections here might not be actually reflections. So we're actually still working on the data. Confidently, I can say that R1 is probably the UG2, because the UG2 is probably 50 meters below the level we are, which is about 500 meters below the surface. So confidently, I can with confidence, I can say the R1 is probably the UG2, but the R2, R3, R4, we can't confidently give what they could be, because our lateral extent could not be able to penetrate there. But the kind of information we see on the data, and then we kind of predict what they could be. But like I said before, we currently still working on the data, and then yes, we are making a very good progress. So this is the interpretation which I try to predict what these reflections could be, which could be UG2, which when correlated with the borehole obtained in the area is quite correlated, which I can confidently say that the R1 might be the UG2. And then in conclusion, I would say that the field was a success in a way that it was a pilot study and then preliminary study to give us initial information of what is obtainable in the area. And then we all know that reflection seismic can confidently be a type of geophysical survey that can complement other geophysical method in any experiment. So we, from our data, we map some additional fault and then stratigraphic intervals, and then we also planning other pilot studies in order to conduct to get more data, and then finally give more accurate results of what is obtainable in the area. So I would like to thank AfricaArray Vets, and then my sponsors, Camera, and then Open Ground, Geolinks, and then Seismic Research Center for their sponsorship. Thank you for listening.
Okay, thank you, Emmanuel. Are there any questions for Emmanuel from the floor? Okay, from chat, Prof. Ray says, thanks, Emmanuel. We are certainly gaining skills in shallow reflection. Few questions. One, what is the cause of periodic peaks in the frequency spectrum? Two, did you manage to download useful data from the nodes? I recall that there was an issue with the configuration setting by the supplier of the equipment.
Okay, thank you, Prof. Question number one, the periodic spike there, we attributed it to fault geophones, which are actually not working, and then they kind of constitute some electrical noise in the data. Then the configuration of the nodes, currently the data from the node is not yet processed, but we currently struggling to get the data from the node in order for we to reprocess it and then achieve the 3D image information of what we initially planned with it. Currently, we are working on it, Prof. Thank you.
Okay, thank you, Emmanuel. Moving on to our next speaker, Lebohang Madisha, was going to give a talk titled Seismic Ambient Noise Study in the Northern Suburbs of Johannesburg, Revealing Patterns in Daily Human Activity, Seasonal Variations, and the Effects of COVID-19 National Lockdown. Okay, Lebo.
It is on Google. It has to log in.
Oh, it is uploaded.
Yeah, that was
Okay, just a moment, guys. We're still trying to load Lebo's presentation.
All right, good day, good day. My name is Lebogang Madisha, and in this presentation, I'll be looking at seismic ambient noise levels in Johannesburg suburbs and showing the patterns in daily human activity, seasonal variations, and the effects of the COVID-19 national lockdown in South Africa. All right. Over here, we see the 3 seismic stations from which I downloaded my data, and these are shown by the 3 red triangles, and Wits is right there as a reference point. So through this, I intend on relating the observed seismic ambient noise levels to possible noise sources within the region of the seismometers. And I will be comparing short period noise levels, which is noise generated by human activity during the day versus at night, and also before and during the COVID lockdown. And I will also analyze mid-period signals in relation to different seasons. This is the setup used. This is our seismometer buried underground, and these are the bits that work the whole thing. Python, PQL, and OpsPy were used to observe and process the data. Now, to process the data, I followed McNamara and Bullen's method, and data was collected from each of the stations and downloaded. Now, the standard procedure for quantifying seismic ambient noise is by calculating the power spectral density. What this is basically a representation of how the signal is distributed along the frequency spectrum. The PSD itself is computed via the finite range vast Fourier transform. Now, a special thing about the PSD and PDF method is that you don't have to remove any of the transient signals that you might record during the period of recording your data. So things like your earthquakes, any system glitches or system transients in general are not removed. Instead, these are kept because of their low probability occurrence. So they won't contaminate the omnipresent seismic ambient noise. So it's okay to keep them there. And then our PSDs are cut into 1 hour segments, which are then further cut into 13 segments, which are truncated, smoothed, stored, and later used to plot the probability of a given power occurring within a particular period. What that was describing was the probability density function itself, or the PDF. And that looks like so. Over here, we have the PDFs for two seasons, summer and autumn. And before I go into the details of these, I just want to point out that this is a period in seconds versus amplitude in decibels function. And these two gray lines that we see over here represent the low noise model and the high noise model, which our noise levels generally stays between. And on the side here, we see our color bar, which shows the probability range of the noise signals that we will be seeing within our PDFs. All right, so when we look at seasonal variations, the focus will be within the double frequency peak or secondary microseism peak. Reason being that this peak right here is generated by oceanic waves that superimpose and generate a gravity wave. So essentially, this peak tells you how powerful or strong the waves are during a certain period in the oceans. So in summer, we see that our double frequency peak reaches a maximum of about minus 115 decibels. And in autumn, this is a little bit lower. We see it reaching a maximum of minus 119 decibels, showing that the oceanic activity between the Indian and Atlantic Ocean is a little bit higher in summer as opposed to autumn in our region. Moving on to winter and spring. Spring has a slightly higher double frequency peak than what we saw in autumn. And in winter, we see that the double frequency peak maximum is slightly lower than what we saw in summer. But above the 120 decibel point, we see that the signal that makes up this PDF in this winter season is made up of mostly higher probability signals. So in summer, we had lower probability signals making up the noise that we see in this region. Now, moving on, I'll be looking at the diurnal variations between lockdown periods and before the lockdown period. So now I'll be looking at the day and night PDF pre-lockdown. Over here, we see our day PDF ranging from 6 in the morning all the way to 6 in the evening, and our night PDF ranging from 6 in the evening to 6 in the morning. This red area over here indicates that this data is missing, which is obviously because we used it to plot this function over here. Now, our main focus when we look at diurnal variations is the cultural or short period noise band right over here. Now, this range of noise is generated by human activities. So our day-to-day activities such as commuting, people going to school, whatever happens during the day affects what we see in this area. So during the day, we see that the signal is composed of more high probability noise signals, which basically implies that the rate of human activity is a little bit higher during the day because it's occurring frequently, and that's why the probability of it is much higher as opposed to at night. Moving on, I will look at the same type of graphs or functions, but during the lockdown period in South Africa. And do take note of the dates. This is during the initial stages of our lockdown in the country. So restrictions were very strict. So before I go to the obvious differences that we see in these PDFs, I just want to point out that over here we have some sort of like stray signal just appearing, and this could be from system transients. And as I said before, these are not removed. And in addition, this could be used to monitor the health of the station So now looking at the differences in the cultural noise period bands during lockdown, we see that during the day we have more lower probability noise signals coming through with our short period noise. And what that indicates is that human activity has decreased. The rate of human activity has decreased because, remember, it was just essential workers who were allowed to go to work and commute, and people were not going to school, people were working from home. So this is expected. And on the other hand, at night, what we see is a dramatic decrease in the actual level of noise that we see. And between the high patrol from the police, people not wanting to get arrested and just not wanting to get COVID, this makes sense because people just stayed indoors a lot more. So activity levels did drop during the lockdown period. Now, the last thing that I will be looking at is the effect of the geographical location of our seismic stations and the kind of data that we are able to acquire from them as a result. So here we see that at the Webb station, we have a relatively higher short period noise level as compared to the other two stations. And that's because this station is located close to a main road, restaurants, and an apartment building. So human activity naturally will be much higher. And on the other side, the Durr station has significantly lower short period ambient noise levels. And that's because this station not only is located in a quieter neighborhood, but also in an isolated area in the yard that it was planted in. And then the last feature that I'll be talking about is this long period noise that we see at the manned station. Now, if you look at the Durr and Webb station, we see that the signal remains well within the low and high noise models, whereas with the manned station, it goes way above. And to explain this real quick, when you have structures like tall buildings and telephone poles or towers of that sort, you have what is called ground tilt that's generated by these structures. And it manifests in the form of this long period noise that we see over here. And in this case, this long period noise was caused by a large tree that this station was buried under. And in conclusion, what we see is that in terms of human activity, high probability signals are observed during the day. Significantly lower levels of ambient noise were observed at night, while the lockdown restrictions were very strict and in effect. And when it comes to the seasons, summer has the highest double frequency peak. Maybe this is due to high activity in the Indian Ocean during the summer season. And as I said before, the geographical location of a station is important in terms of the kind of data that you're able to acquire, the quality of the data. And ultimately, all of this information will be useful in designing a seismic network that can better monitor and detect earthquakes. And thanks to all of you. Are there any questions?
Okay, thank you, Lebo. Are there any questions for Lebo? I think there's a discussion happening in the chat or something. I think these are related to Emmanuel's talk. And then Prof. Ray says, interesting stuff. Proves that Sue is the party animal. With regard to the ocean wave activity at 5 seconds period, why is it called a double peak frequency? A double frequency peak?
Why is it called double frequency peak? That's a good question. I don't actually know. I just know how it's generated and that it's the higher of the two frequency peaks. the single frequency peak occurs a little bit later during it within the PDF. So I don't really know why it's called the double frequency peak.
Okay. Can I make a comment? When you have to double peak frequency, because I did something like that in my PhD, which is the first paper, when you have double frequency, double peak, which are double fundamental frequency, the cause of it is normally when you have two stratigraphic layers on the near surface. So because normally when you have a peak fundamental frequency, it means that you are picking the top layer, we call it overburden thickness, or the top layer, the top sedimentary layer, or the weathered layer. So that is for single, but when you have double peak, it means that it's picking two stratigraphic layer on the near surface.
And a double frequency peak in this case is generated by two waves of the same amplitude superimposing and generating a gravity wave. So I guess in that case you have, that would be the reason why it's called double frequency peak.
Yeah.
Okay, cool.
Okay, thank you very much, Lebo. Okay, up next, we have the student chapter of the EAGE, and that's going to comprise of Nandipa and Nombuso, who are also today's organizers of this event. So they've been quite busy, so let's give them some time to prepare. They're coming up soon. And yeah. Prof. Sue says, very exciting to see this data. Can we correlate some of the noise with load shedding? So I think you can have that discussion later. But thank you very much for that. Go into it.
Hi, I'm not sure if everyone can hear me. Am I heard? Hi, everyone. My name is Nombuso Maduna. I will just be giving a little brief talk of what the WITS EAGE student chapter is. The EAGE stands for the European Association of Geoscientists and Engineers. So we have a student chapter here at WITS. We're pretty young and still in our infancy. So we'll just show you what we've done so far and what we hope to do in the near future. So basically, the whole purpose of the EAGE student chapter is to promote geosciences and specific branches of geosciences in the oil and gas industry, mining, environmental and civil engineering, and to promote global EAGE student activities within the local region. So our goal is basically to connect students at the University of the Witwatersrand with a global network of geoscientists and engineers, and to organize educational events and to strengthen the knowledge, skills, and network of students. And basically to increase the number of EAGE members that we have at the university. And to increase the university's involvement in the EAGE community, basically by submitting paper submissions for workshops, conferences, journals, and participation in other student activities. So just go to the next slide. Great. Okay, so we're the first EAGE student chapter in South Africa. In fact, as you can see here in this map, for the most of Southern Africa. We located obviously at the University of the Witwatersrand, Johannesburg, and we are excited to see basically what we will continue to do with EAGE in the future. So our faculty members, we have Dr. Michael Westgate, he's our faculty advisor. We have myself, the president of the student chapter. We have Nadipa here, which is our vice president, and Muchafa, our treasurer, and Ritable Dao as our secretary. So the first activity that we kicked off with the EAGE was back in 2020 when we basically were showcasing a career expo in Limpopo at a high school, not a high school, but at a high school there. So it was very interesting to get the student engagement and all of that. So what we were showcasing there, we took like a team of us and we showcased 3 different things. So one was geology, another was geophysics, and paleontology, all under the School of Geosciences. So you can see here how the students have been interacting at the school. They were very excited. You can see here in the bottom corner, they were very excited to learn what a microscope is and to see the minerals and all of that under the microscope. They were, of course, very excited to see skulls. And at the top corner over here, we were basically just showing like how magnetics works and the structure of the earth and how geophysics would work.
So keeping in line with the general development of the EAGE over time, it was initially established in 1951, but as the European Association for Petroleum Geosciences. And then eventually with the development of the industry as a whole, where things started becoming interconnected and it wasn't just about petroleum anymore, it developed into the European Association for Geosciences and Engineers. Now, through all of this, it's become such a big establishment that this year they hosted the 82nd meeting that was hosted as a hybrid conference in Amsterdam. So as a student chapter for an organization like this, we are trying to keep in line with the kind of work that they're doing that is interdisciplinary and also spans all kinds of technology that gets applied in the geosciences industry as a whole. So as part of the activities that we conducted last year, if you can see in this picture, this was post-COVID, but we still kept going. We were involved, led by Prof. Sue and assisted by the WITS video team to record some of the geophysical methods that we apply in field school and the other field work that we do. So this involved quite a few of our own student chapter members, as well as the postgraduate students that are within our department. These videos can be found on YouTube, and they span equipment such as the GPR, resistivity, as well as the DGPS. And a lot of these videos were actually recorded in the field on field school. So they do involve quite a lot of actual student participation. Speaking on that as well, we've been very involved in the annual AfricaArray field school. It wasn't as big last year because of COVID, but we got to pick it up again this year very nicely. And this involves the participation of postgraduate students as demonstrators. So this gives us a very nice and open opportunity to apply the skills and the knowledge that we've come to learn across time in the department, all the skills that we've come to learn and understand from our supervisors and such. And as we interact with the younger students, the honors students, then we start building their capacity as well as transferring the skills that we've come to learn as well, which is a fundamental block for the EAGE as a whole. In that as well, so from the stuff that we learn in the field, and now we come back here and under supervision of our supervisors and things, our postgraduate students, the PhDs and MSCs, participated this year in the Near Surface Geoscience conference. And in order to pass this on, which is our mandate as a student chapter, we hosted a showcase within the department where the postgraduate students presented their work to the honors students as throughout geology and geophysics, so that they could see the kind of opportunities that are available and the kind of skills that have been gained throughout the geophysical career.
So right now, the latest event that we have planned as a student chapter, together with the help of BTG and WSGS, is this 15th AfricaArray scientific meeting. So we basically form the main organizing committee and making sure and making things work and showcasing the global AfricaArray community research. So we did a lot, and we hope that there will be more that will be done in future. And then I'll take it off to my faculty advisor.
Thank you. Yeah, so looking forward, this is really only the beginning, and I suppose the three pillars that will remain central to the EAGE student chapter are the three pillars that should be the beginning of anyone's career, and that's networking, capacity development, and project collaboration. And with this EAGE student chapter, that will be facilitated by a two-way road, a two-way link to Europe, where we both get to showcase what's being done in South Africa so that we're not isolated, but also get to take from these international collaborations what cutting research is and techniques are being implemented and bring them back with us. This is particularly important in the hard rock environment because that's one of the few or one of the important things that we share with a lot of the EAGE projects is that they typically work in hard rock environments similar to what we have. So how does this actually play out? What are some of the ideas that we have? Well, firstly, the student chapter can serve as a local hub for anyone who's interested in geophysics, as the ladies have already demonstrated that any potential students and people who are interested can have a place to look and be part of both a community and a technical training program. It can also serve as the students can be our ambassadors, our young ambassadors in overseas conferences and in international showcases, where we can show from an early on stage in the career what kind of techniques we're doing. And then finally, the capacity development, which is very important here in South Africa, like what can the students do that will uplift previously disadvantaged communities, and what kind of practical applications of the techniques that we're developing here can we implement in rural areas or poor areas and the like. And so those are just a few ideas of where we'd like to take the student chapter. But AfricaArray and what the ladies have shown is just the start, and we're very excited at the birth of this new initiative. Thank you.
Okay, thank you, guys. Are there any questions for the EAG? I don't see any. So I think that's the end of this session. I think we're going to have a tea break right now. And then we'll be back at 15:45. So please do come back. We have 2 international keynote speakers. So we're going to end off the day on a big bang. So please do join us after. Thank you very much, guys.
Thank you.
Okay, thank you very much, guys. Now on to our last session of the day. We have two keynote speakers, as I said. First one up is Professor Hiroshi Ogasawara from Ritz University in Japan. Just a brief introduction on Professor Ogasawara. Since 1992, he has collaborated with 13 South African deep gold mines, WITS, IMS, CSIR, and CGS. Hiroshi and his Japanese colleagues initially endeavored to elucidate the earthquake generation processes at the closest proximity of the hypercenters with dense sensitive sensors. During 2010 to 2015, he and Professor Ray Durheim co-chaired and enhanced bilateral research projects under design by Japanese and South African government to mitigate seismic risk in mines. Having geomicrobiologists and geologists, he and his colleagues from Japan, South Africa, the US, Germany, Switzerland, India, and Israel accomplished drilling and full core recovery from the seismogenic zones detailed in the invited talk. So without further ado, Hiroshi, if you may please join us.
Yeah. Can you hear my talk? Can you hear me?
Yes, we can hear you, bro.
Okay. And can you see my screen?
Yes, we can see your screen. Thank you.
Okay, so let me start. And don't you mind if I use this mode? And because it is very convenient for me. Okay, so let me start. Unusual sinistral magnitude 5.5 earthquake took place. And when we intersected the magnitude 5.5 aftershock zone, we didn't know what we are going to talk in this workshop. But anyway, thank you very much for inviting me to give a talk to everybody. I miss South Africa very much, and I hope this talk can be my sincere greetings to everybody. And I first explain about some background of the earthquake. This earthquake was very nicely monitored by dense surface strong motion meters, with maximum acceleration was 2.3 G. And the dense underground seismic network located lots of aftershocks concentrated on the southern end of the rupture zone. And these are the main slip area, differently located from the dense aftershocks. And the usual mining horizon earthquake take place on normal faults, as everybody knows. But this was below the mining horizon, and it was sinistral. So everybody thought, why? And before the drilling into the aftershocks of the Orkney earthquake, we expected very fresh ruptures in the brittle regime, and the rheology and the stress of at the Moultrie cracks tip in the brittle regime, and the microwave activity in association with seismic hydrogen generation. But it was found the Orkney earthquake with unusual sinistral faulting below the mining horizon was very special. These are the colleagues who worked with researchers and practitioners and from Japan and South Africa, Switzerland, USA, Germany, India, Israel, and Australia. And it was done under the financial support by ICDP and many other international funding organizations, and facilitations from South Africa and Japan and other countries was essential. And this talk is also for tribute to T.C. Onstott, a legend of microbiology, geomicrobiology. Sadly, he passed away on 19th of October 2021. Now, still now, this esteem is in great grief, but we continue to make every effort to make TC's dream come true at the Mopkot mine. And he started his research in South Africa in 1996. And greatest findings include live microbes at depth, resulting in being listed among Times Magazine's 100 most influential people in the world. And this is some more details about his findings in Moab-Khutsong mine. And we drilled 2 holes to intersect the magnitude 5.5 aftershock zone, but we couldn't intersect the magnitude 5.5 aftershocks with hole A because it deviated too much. But we intersected the aftershock zone in hole B. But the hole A intersected very interesting dike, which was very well mapped on mining horizon. And T.C. Onstott and his colleagues found ever saline and older brine at the in hole A. This is the isotope contents, and showing the brine they found in hole B was very unique, not a metallic water line, not on the metallic water line, but and above the Kid Creek brine. And this is the and this figure shows the Moab-Khutsong brine is the end member of the brine they have collected in South African mine. This is the seawater, and the other include the dromites and tautoda and kloof and beetrix and the amponena and others. So they were very much excited to have this brine, and they were about to look into more detail about this brine, but this is sadly passed away. So we made decision to make every effort to continue to this is the dream come true. And to honor him, we named the dike as an Onstott dike, and it contains methane on the mining horizon haulages, and hypersaline brine in hole A, but very curiously, it is less saline in hole B, and hole B water doesn't flow out, while hole A brine flows out. So we have to look into the difference between hole A water and hole B water. We start logging again in January 2022. We look forward to find something very new from this logging. And original main science target of this drilling project was the seismogenic zone in pink. And this is another another figure, and showing the seismogenic zone. And the greatest challenges include Sanders Fault Observatory at depth, but the drill hole didn't reach the streaks of the seismicity, and it was above the slow earthquake depth range. So lots of questions remains. If we want to reach the seismogenic zone, and we also want to measure stress reliably to know what is going on, and the mystery of streaks as well. And microbiologists are interested in the deep biosphere. However, SAFOT drilling and the other international drilling only in this range. Most are in sedimental cover. SAFOT is also in soft rock area. And this is another representation of the other international drilling project. It is in smectite or elite area. In contrast, our South African gold mine project and ICDP DAFSAM project and SAFTREFSAM digitized Scoop 4 project reviewed the very much detail about the seismogenic zone. And the Moabuk zone result suggests the material recovered is at the depth range, something like this. So we are very much excited about this. And seismic reflection data analysis shows the velocity range is above 6 kilometers per second, while SAFOT VP distribution is something like this. So our drilling is was going on in this VP range. And this is again the aftershock zone and our drilling, and this is the logging, and this is the core. And we are now have the central critical, the most critical section at Coach Core Center. And we are now busy with analyzing data. This is the very compact stress measurement new technology to delineate spatial variation in much details. This figure summarizes our findings, and the highlighted in light blue is the hypersaline brine onslaught found, and the yellow represent the stress concentration area, and the red represent the location where we intersected the aftershock zone and the talc and other altered mineral from olivine and the pyroxene. And this is again the onslaught dike, and we are going to look into detail. So in 2019, we could have Dakaro and Difa at Kochi Core Center to carry out X-ray, CT scan, and MSC, mostly for non-destructive investigation. And we had to have a long intermission. We couldn't visit Coach Core Center during this period, but finally we could have 1 week opportunity to be at Coach Core Center now. And this time we are carrying out a destructive test. We could have Yohei Suzuki, professor from Tokyo University, who is a NASA Mars Sample Return Working Group members with TC and Tom. And he brought an FTIR, an instrument, we scratch this small portion to have a very small amount of powders. We put powder here. Then we have the infrared absorption spectra to identify minerals. We also carry out XRF scan for all in amplifier core. We also make thin sections, and we are looking forward to have a very interesting data. And we have to mention the great success by Sianda and Azama, who successfully published the papers, and congratulations. So we hope we can continue good collaboration also in 2022, and initiated by Holby logging in January. And hope we can visit South Africa again, and we can also have South African in Japan again to work with. So I hope we can enjoy South African gold mines, invaluable laboratories, deep underground for geoscience. So this is the enlarged view of his FTIR instrument. Okay, and this is the brief summary, what we have accomplished, and successful drilling, and downhole logging, and water gas sampling, and elucidation of stress variation in stress. And everything was done by 2019. It was very nicely followed up from last week when we could be in Kochikwa Center. So this is all I wanted to talk to you. Yeah, thank you very much for your attention.
Thank you very much, Hiroshi. It's good to see that South Africans are welcome in other countries. Are there any questions for Hiroshi? I don't see any in the comment section. So I think it's safe to move on to our next speaker. Okay, just a brief introduction. Okay, thank you very much. Our next picture is Sarah Stamps, all the way from University of Virginia Tech University in the USA. Just a bit about Sarah Stamps, professor. She's an associate professor of geophysics at Virginia Tech Department of Geosciences, specializing in geodesy and tectonophysics. She and her research group members produce and use GNSS positioning data to observe how the Earth's surface moves. They also use computational modeling to elucidate the physical processes driving the Earth's surface motions. The data analysis and computational modeling aspects of a research program have applications in volcanic, seismics, and coastal hazards, as well as the plate tectonic theory. Her study areas include Tanzania, Uganda, Madagascar, Malawi, China, the East African Rift System, and the Chesapeake Bay in the USA. So Professor Stamps, if you're ready, please, you may go ahead.
All right, thank you so much for the introduction. I am delighted to give this presentation today on a new present-day kinematic model of the East African Rift System. As was stated, my name is Sarah Stamps. My pronouns are she, her, and I'm actually presenting from Blacksburg, Virginia, where we cannot separate the history of colonialism and the forced removal of the traditional custodians of this land, the Tulo-Monacan nations. So I pay respect to the Tulo-Monacan nations and the former enslaved people in this area. Today's presentation will include some GNSS data, like the one that's shown here in the background. This is a station that we have set up in Madagascar. That was from 2014, and it's one of many stations that's incorporated into the work that I'll present today. There have been several key contributions from Corne Creamer, Rui Fernandez, Tahiri Rajanarasan, and Gerard Rambalamanana for the work I'll be presenting today. It's been largely funded by the National Science Foundation in the US, as well as funding from the National Geographic Society. And we've received technical support and leverage data from UNAVCO as well. So my talk today has 4 parts. I'm going to review the FAIR data principles. I'll give an overview of the East African rift system, and then I'll talk about the key part of the talk, which is redefining the kinematics of the East African rift system, and then I'll provide a summary at the end. So a little bit about FAIR data principles. FAIR stands for findable, accessible, interoperable, and reusable. These are principles that are chiefly applied to data, but they're now being applied to software as well. They were published by Wilkinson et al. In 2016, and it really aims to help make data more available for reproducible science. There are quite a number of repositories for finding and archiving data in the geosciences. For example, there's Pangea. A more general one is Zenodo. There's also Figshare as well, that's very general. IRIS provides archiving for data, as well as several other types of Earth models. UNAVCO provides data for several geodetic products, as well as some other data as well. And then I bring this to your attention, not only because AfricaArray produces a lot of data, but also if you're going to be publishing, there are a lot of publishers who have adopted FAIR data principles. So I'm going to leave you, provide you with this link here. And this is a website that helps people find repositories that are useful for their data. And then you may also find repositories of data that could be useful to you as well. I acknowledge many institutions who've made their GNSS data available for public use. And these are several institutions that do that and have made this work possible that I'll present today. So a bit about the East African rift system. We know that it's the active divergent plate boundary between the Nubian plate here in the west and the Somalian plate here on the east. It's quite large. It stretches from the intersection of the Red Sea, Gulf of Aden up here in the north, all the way down to south of South Africa, where it intersects with the Southwest Indian Spreading Ridge. And then it also stretches from the Eastern Democratic Republic of Congo all the way to Eastern Madagascar. We have pretty good constraints on how fast the East African rift system is spreading. It's approximately 1 millimeter, actually less than 1 millimeter per year in the south, and that it increases in how fast it's opening in the north to about 6 millimeters per year. Recent work has shown that there are now at least 4 microplates between the Nubian and Somalian plate systems. So early in the 2000s, we found the Victoria microplate, the Rovuma microplate, and the Luanda microplate were resolved with GNSS data. And then just recently this year, the Sand microplate has also been resolved with GNSS data in a paper by Wedmore et al. Just this year. So some more background on the East African rift system. We know that it's quite seismically active. This is a subset of earthquakes shown as red circles from the National Earthquake Information Catalog. And then we also know it's volcanically active with an uneven distribution of volcanoes. So more volcanoes in the eastern branch and less volcanoes in the western branch. Could I confirm that you can hear me okay? I had a...
Yes, we can hear you.
Okay, thank you so much.
Yeah, we can hear you.
Perfect. Okay, and I wanted to make one note about the term East African Rift versus East African Rift System. You may see in the literature that these terms are used sometimes interchangeably, but usually when people are talking about the East African Rift, they seem to be focused on the continental part of the East African Rift system. So I just wanted to point that out, that often you'll see East African Rift and it usually is focused on this section. But if we think about the whole system, it's actually much larger than the region that's often talked about as the East African Rift. Okay, so I'm going to go into the new model of a new kinematic model of the East African Rift system. So early on, back in 1994, a paper was published by Stein and Gordon, and they were suggesting that the East African Rift system was wide and diffuse. And this red zone here and the yellow zone represent these diffuse zones of deformation. A few years later, Chris Hartnedy suggested this model on the right, where he said that it's more likely that we have rigid blocks in between the Nubian plate and the Somalian plate that are bounded by narrow zones of seismicity. So he assessed where there were earthquakes between the Nubian and Somalian plates, and those bands of seismicity are represented by the gray areas in this figure to the right. So these are two very different models for how the Nubia-Somalia plate system is breaking up. So one that's wide and diffuse, and then one where we have rigid blocks bounded by narrow zones of seismicity. So in order to differentiate between these two models, we need observations of how the surface moves and deforms. So we physically measure the surface motions using GNSS observations. The figure to the right is a velocity solution shown as the black vectors from Soria et al. 2014 for the East African Rift system. And then in the figure to the right is the Wedmore solution that has more data in South Africa and some more in West Africa, because his focus was more in the southern parts, the southern region. So after we get constraints on how the surface is moving and deforming, we can use that data to test for rigid plate motions using codes like tDefNode or DefNode. So in the figure to the left is the kinematic model of Soria et al. Based on DefNode, which is the predecessor to tDefNode, and I'll talk about that a bit later. But it is a code that allows you to test if a region is moving rigidly or if it's moving by diffuse deformation. Wedmore et al. In the figure to the right used tDefNode, and they were able to resolve the sand plate, which is a new development. So a little bit about GNSS. GNSS stands for the Global Navigation Satellite System, and there are many GNSS systems. The one that's operated by the US military is the GPS system, so the Global Positioning System. The figure to the left has the Earth in the middle and a depiction of the orbiting satellites of the GPS system. So we use GPS, or one may collect more signals from different satellite systems. But in this work, I focused on the GPS system. Okay, so we do measure that the surface motions with, thank you, Sue, for the comment in chat. I'll get to that at the end. So a little more about the GPS system. It is operated by the US military. There's about 35 operational satellites orbiting the Earth. And then it's transmitting, we're transmitting radio signals to the Earth's surface, which is shown in this figure to the left. So the red lines are representing the radio signals being transmitted from the satellites. I bring to your attention this phase equation. So this is the key equation that we use to calculate positions of the Earth's surface from the GNSS or GPS data. And I just want to draw your attention to a couple of variables in this equation. So here we have ion, and then we also have trope, T-R-O-P. So the ion part is about the ionospheric delay, and the trope part is for the tropospheric delay. So these signals coming from the satellites are traveling through the ionosphere as well as the troposphere. The ionosphere has a lot of electrons in it, and that actually slows down the GNSS signal. And the troposphere has a lot of water vapor in it, and those water molecules also slow down the signal. So these are just two key corrections that have to be made to the data in order to get the millimeter precision positions and precise velocities. So we use research grade software to solve the phase equation. A couple softwares are listed here. Gamut Globe K, that's the one I use and people in my research group use. Bernice, and then also Gypsy X. Once we process the data for positions, we get one position per day, and that's represented by these blue circles. This is a time series with day of year along the x-axis and then displacement along the y-axis. So once we have a very precise position, we can essentially use the velocity equation, which is distance over time, to estimate a velocity. There are two types of GPS systems or GNSS systems that we use to observe tectonic plate motion. The one on the left is a continuous GPS system. This one's installed in Uganda. So this system stays ideally forever, and it's collecting data continuously. And then the other type is campaign GPS, also known as episodic GPS. So we have a benchmark in bedrock, and we repeatedly measure that for a period of like 3 days, and we'll measure it 1 year and then come back a year later or a couple of years later and remeasure the same position to see how far it moved. So with this new kinematic model, I was aiming to address where the Luanda-Somalia plate boundary is located. This figure to the left is showing plate boundaries as the black lines. And Madagascar here has the Luanda-Somalia plate boundary passing through it. And this is a model from Saria et al. In 2013. So the boundary here is very unresolved. There was only one station available in Madagascar at that time to constrain the kinematics. So we have a lot of new data that I'll show. And then another question that I addressed was about the rate of the Somalia plates. Because I had a paper come out in 2018 that indicated the Somalian plate rotation rate might actually be faster than these earlier models. So let's talk a little bit about the active tectonics of Madagascar. This map here in the middle is highlighting quaternary features. So in yellow are sedimentary basins. In particular, we have the Alautra Anke Rift here in the kind of central east region, which is an active rift. We also have the Morondava Basin down here in the southwest, which is also actively extending. And then the Ranantsara Shear Zone here in the central south part of Madagascar. Schurz et al. Suggested that it might actually be reactivated and actively extending. And there are some mapped faults in this region that would support this hypothesis. I've also pointed out that there's some quaternary volcanism as well in Madagascar. These are these red zones. And it's a bit interesting because all of this volcanic activity seemed to have started around the same time. And it's still a mystery as to what caused all of this volcanism to happen almost coincidentally in time. With respect to earthquakes, these are focal mechanisms in the map to the right from the Global Centroid Moment Tensor Catalog. And they are showing that in Madagascar itself, it's largely extensional faulting with some strike slip here and then some thrust faulting. There was a more recent paper by Rakatandrabe et al. In 2020, where she leveraged a network of seismometers deployed across the Comoros and Madagascar called the Makamo network. And she resolved a lot more earthquakes happening in Madagascar. So the focal mechanisms are shown in black and white, which are dominantly extensional, but there is some complexity as well. So some areas of compression and strike slip movement. And then also the red circles are showing the pervasive amount of earthquakes that are happening in Madagascar. So it is pretty seismically active and tectonically active as well. With respect to the Luanda-Somalia plate boundary in Madagascar, there have been several published models. To the left is Kusky et al. In 2010. He suggested that there's a wide diffuse zone of deformation in Western Madagascar. Argus et al. Had a plate boundary going through the Ranatzaru shear zone and going further north and west than the model of Soria et al. In 2014. And then my paper in 2018, we modeled all of Madagascar as deforming. So in order to answer the questions that I had posed, we used GNSS velocities, specifically the GPS signals. I processed data for a total of 25 sites that I used to constrain a kinematic model. There were 16 sites that were predefined to be on the Somalian plate, and they've been well resolved to exist on the Somalian plate. I had 5 episodic or campaign GPS stations on Madagascar, and then also 3 continuous sites on Madagascar. And then there was 1 continuous site in the Comoros here, MAYG, that was available, but we only used data up until May 2018 because there was a volcanic event happening offshore that affected that data. In this map to the left, red are GNS or GPS stations that had previously been used in kinematic models, although we did extend the time series. The yellow vectors represent data that's completely new for kinematic work. In this velocity solution, I was very focused on those 2 questions. So where's the Luanda-Somalia plate boundary, and then how fast is the Somalian plate rotating? And then I've just sketched in the sand plate because we now know that this one exists as well, but it was not the focus of this work. I was more in the eastern part of the rift system. So to process this data, I used Gamma Globe K, and I used an approach that's published in Soria et al. 2014 and Rui and Stamp's paper in 2019. One thing that's different is that I characterized the noise by using Hector, which is a very nice program. It allowed me to model white noise and flicker noise for all of the stations. And then for continuous sites, I applied the Gauss-Markov equation to calculate time correlated noise. In order for the velocities to be incorporated into the kinematic model, I required that the uncertainties, the 1 sigma uncertainties, be less than 1.5 millimeters per year. All of the data, the solution is available as a supplement to my paper, as well as on Figshare, and also in GMT-PS fellow format at this FTP site through UNAVCO. So this velocity solution is absolutely fair. For the kinematic modeling, I use tDefNode, and it is an openly accessible software program that's available at this link. tDefNode is designed for angular velocity estimates, assuming block rigidity. You can also test and calculate fault locking. So you set up the model using a diagram over here to the right as an example. So the blue would be elastic blocks, and then the red lines would represent the faults bounding those blocks. For the approach I decided to use freely slipping block boundaries because there was not a lot of relative motion across the block boundaries. And I was very interested in just testing the plate rigidity hypothesis. So I did not solve for fault locking. I did a linear inversion of the GPS velocities to calculate angular velocity vectors for the different blocks. So the model input files and output files are available on Figshare for open access. There's a citation down here to the right and a screenshot of the website. If you are welcome to go and download those files and reproduce this work. So the model consists of 6 plates or 6 blocks. The blocks 1 through 4 here are constrained by the Soria et al. 2014 kinematic model. And then I varied the Luanda microplate and the Somalian plate geometries and then the number of GPS velocities for these plates to address the questions. I'll present now the experiments. So the first step was to calculate a base model of Somalian plate motions that I could compare all the subsequent models to. So for this one, in this map here, I have the data shown as the black vectors and the model shown as red vectors with 95% uncertainty ellipses. And then the statistics up here for the reduced chi-square, the weighted root mean square, and the normalized root mean square are shown here at the top. So I ran the first experiment to test if Madagascar moves rigidly with a Somalian plate by adding all the velocities on from Madagascar. And the answer is no, because statistically the fit significantly degraded when we added in those velocities. So then further experimentation, I tested each site on Madagascar and the Comoros individually. So here is when we add in the Comoros to see if it moves rigidly with the Somalian plate, and it does not. And then for all the stations on Madagascar, there were actually 3 that had similar or better statistics when we compared with the Somalian plate base model. So ABPO, ANTA, and VOIM, all these 3 sites were consistent with Somalia plate motion. So these results suggest that there's one piece of Madagascar that moves with the Somalian plate, and then the rest of Madagascar is deforming here in the central and northern parts. But there's still a question about southern Madagascar and if it moves with the Lawandle microplate. This configuration of deforming zones versus rigidity is pretty consistent with the distribution of seismicity as well. So there's less seismicity in this piece that is rigidly moving with the Somalian plate, according to the recent work by Rakatandrabe in 2020. So I did some further experimentation to test if southern Madagascar moves with the Lawandle microplate. So to do that, I had to add in some geologic data along the Southwest Indian spreading ridge because we only had 2 sites in southern Madagascar to constrain the model. And I used the F-test statistic, which was also used by Stein and Gordon in 1994, which is shown here. So this allows us to statistically determine if a new microplate is warranted when you add that to your kinematic model. So we do that test in the figure to the left. This is our Somalia plate model. So if we included all of that data and then assumed only it moved with the Somalian plate, these are the statistics. And then if we add in the Lawandle microplate, which is shown in the figure to the right, we get improved statistics. And then according to the F-test, it does indicate the Lawandle microplate is warranted with this configuration. So to summarize, we have found in the figure to the right is the new kinematic model that focuses on the eastern part of the East African Rift System. The red vectors are showing Somalia plate motion with the angular velocity vector shown as this red star here. And we did find it moves faster at 0.076 degrees per million years than previous estimates. Here we also redefined the geometry of the Lawandle plate with the boundary passing through the Ranat-Sata shear zone, and a new angular velocity vector as well for the Lawandle microplate at 0.045 degrees per million year in this yellow star. We were able to resolve this broad deforming zone that extends from the eastern Rovuma plate boundary to parts of Madagascar, which is about 600 kilometers wide. So this work suggests that there's a bit of a combination between those early models of the Stein and Gordon 1994 and the Chris Hartnett model. So the East African Rift System is extending with both narrow strain accommodation and diffuse deformation. And then finally, the software is open access, the velocity solution to constrain this model, and all of the model files are available open access. So I'm happy to take questions now.
Thank you very much, Prof. Stamps. Are there any questions from the floor? I don't see any questions from the floor. Prof. Webb says, can NSAR be used to resolve motion at some of these boundaries, essentially slow slip?
So INSAR has the capability to certainly cover wider areas. The resolution of INSAR data is less than GNSS or GPS at this point. So most of the INSAR satellites can get you a couple of centimeters of precision in the horizontal and vertical, but it's possible you can combine INSAR and GNSS data and resolve you can better resolve the surface motions. So I would say the combination of INSAR and GNSS can be used to resolve these plate motions. I say you need the combination because the plate motions are pretty slow in East Africa and along the East African Rift system. So they're generally below that kind of 1 centimeter resolution. But if you combine the two, I think you have a good chance at using INSAR. Okay.
Can I just ask another question?
Yeah.
On the top part of the Bangalore-Ranatsara shear zone, sorry, I'm using the wrong.
Oh, we heard you. Oh, we don't hear you anymore though. So I don't hear Dr. Webb anymore, but I'm gonna also tackle Andy Nyblade, Dr. Nyblade's question in the chat. He asked how well resolved is the northern boundary of the sand plate. I think that's not very well resolved. I think probably the region through here is fairly well resolved. I don't think it's extremely well resolved at this point. I would say that is not a well resolved, because these plate boundaries really depend on where you have GNSS data available. So yeah, I would say not extremely well resolved.
Yeah, Sarah, I was just talking about that east-west line at the top of the Ranatsara shear zone. You don't follow up along the Bangalova portion. You just go directly east-west.
Like
I'm
up
just
here?
wondering I'm wondering what the reason for that is.
The reason for these zones is really the distribution of the GNSS stations at this point. I think this is an area that could certainly be improved in the future using more constraints from like structural geologic mapping and distribution of earthquakes. But at this point, it's largely based on the distribution of where we had GNSS data to constrain the region. So that is certainly an area for improvement. And I hope that that can be improved in the future as well.
Oh, that's great. Thanks. I just wondered if there was a feature there you knew about. Thanks.
You're welcome.
There's one last question from Prof. Durheim, and he says, what criteria must be met to declare a new microplate?
Yeah. So the approach we use is the F-test. So we're that is how we're defining how we're resolving these microplates. So you can build your kinematic model. You can test if a plate geometry exists, and then it is that F-test that allows you to determine if it's warranted. So when you're doing modeling and you add in additional parameters, then it's possible your statistics will improve. But you need to know if it's significant. Is it actually warranted to add more parameters to your model? And that's where the F-test comes in, because it allows us to ask that question. I hope that answers the question. We could definitely do better, I think, as a community in how we define new plates. But from a modeling perspective, the F-test is how we do that.
Yeah, that satisfies me, Sarah. I mean, I just don't know. That's a question asked from ignorance, and I'm just curious about how this whole process is followed. I mean, as we discussed, when it comes to stratigraphy and declaring new units or formations, it's quite a formal process. But here in plate tectonics, I think, as you said, it seems to be a little bit less defined.
It is, especially the naming. It really, at this point, it's like who publishes first as to who gets to name the plate. Yeah.
Yeah, and even there, I see it's called the sand plate. Now, I suppose I know Branko and Corner and I named a terrain called the sand terrain in 2018. So now there might be two different entities with the same name, one a microplate and another one let's say a basement terrain. Now, I mean, I don't really mind, but it just means you could get a proliferation of names without any real order there.
Thank you so much for the invitation to give this presentation.
Okay, thank you very much, Prof. I think that was our last talk for the day. I don't know if there are any further questions or comments. I don't see any. So yeah, I think that brings the session to the end. Yeah, everyone who's here in person is welcome to join us for dinner. I think it's at Origin Center. And then, yeah, thank you to everyone who attended virtually and in person. Really appreciate it, guys. And I think we'll see each other tomorrow at 9 a.m. So please do come around. It's going to be an exciting session. I see a lot of interesting talks coming up. And yeah, thank you very much, everyone.